Resume recording. Okay, so let's do that all over again, right? Here you go. Let's do that all. You know, if I don't share the screen, you cannot see me doing the explanations, right, with the hand. But well, okay, that's the transverse wave, right, that we covered. No, there are all sorts of waves, mechanical waves, electromagnetic waves, matter waves as well. And now that we finally verified the existence experimentally, right? Verified experimentally the existence of gravitational waves as well, which was predicted by Albert Einstein in 1916. So we finally managed, almost 100 years after Einstein prediction. Yeah, 1916, the first direct evidence detection of waves, of these waves, right, came in 2015, 99 years after the prediction by Einstein. People are talking about a Nobel Prize, whoever detected, the group that detected those waves might be able to win the Nobel Prize. We'll be able to talk also about matter waves that has already been demonstrated a long time ago. And Einstein didn't predict that. This was a theory that was developed by other scientists. And you know, the wave in a string is a transverse wave. Electromagnetic waves is also a transverse wave. And the water waves, yeah, they are transverse waves as well. If you look closely at the waves, the ripples in a pond, you can see that there is a disturbance in the vertical direction of the water, right? That's why we see those waves coming towards you at the beach. So that's also a transversal wave, transverse wave. And longitudinal waves, I explained to you. Okay, let's see. Here is another type of wave, is a pulse, okay, that we can generate in a string. And the nice thing about any wave is that they can be described in terms of planar waves, in terms of sines and cosines. This pulse that you see right in here doesn't look like a sine or cosine. However, it can be described mathematically as a summation of sines and cosine waves. I'm not proving here, but I want you to remember that, okay? So let's, and here is our planar wave, a sinusoidal wave. We're gonna just summarize what we have done so far, okay? I'm gonna keep on switching back and forth between my notes and the book in there. Okay, summary so far. Here you go, transverse waves versus longitudinal waves. Longitudinal waves. Okay. So, transverse waves. Transverse waves. What are transverse waves? You know, the material, the medium. Let's not say the material. The medium is better. Okay, the medium through which the wave propagates, oscillates in a direction transverse to the direction of propagation of the wave. That's the qualitative idea here. It's important that you have a good qualitative vision of all those things happen, and also, you know, a mathematical vision as well. Both of them is important. Both of them are important. Okay, example, right? Example. Waves in a string, right? Waves in a string. In this case, the points of the string oscillates up and down. Okay? The point of the string oscillates up and down, whereas you have, I would say, the illusion, right? Illusion that something else propagates along the horizontal direction. Along the horizontal direction. This something, is the immaterial energy of the wave. So the material points oscillates. The material points oscillates along the vertical direction, whereas the immaterial energy propagates from one end of the wave to the other. It's like that. That's the idea that you must have. Okay. For the case of a longitudinal wave, for the case which we haven't covered yet, okay? For the case of a longitudinal wave, the medium vibrates along the same direction of propagation of the wave. The material medium is along the same direction of the propagation of the wave. So in the case of air, for instance, the air molecules are oscillating in this horizontal direction, and then you have this illusion that there is something propagating from one end to the other one. Okay? It's not actually an illusion, but that's how I like to interpret that. And this something is energy. And it is energy that can be used for important things, okay? So that's what we have here for the transverse wave. And then we look at the wave speed. Here you go, the points propagating up and down. Right? And here you go, here's the sound wave propagating, the molecules propagating, or the molecules, not the molecules propagating, but the molecules oscillating in the longitudinal direction. Okay. And I'm going to elaborate a little bit more on that. We talked about wavelengths and frequency. Here's the solution for a wave, for the wave equation. That is the planar wave. You gotta memorize that. Okay. And there is another way of expressing the same argument here, right? Can be K open parentheses X minus VT. I think that the X minus VT format is far more intuitive than this format here of the argument, of the sign. Okay. And wavelength and angular wave number. Angular wave number, they call it. The K is the angular wave number. I like to call it wave number only. Okay, angular wave number. They call it angular here because of the 2 pi upstairs, okay? But many books call the same wave number instead of angular wave number. More students coming in. Okay. And that's the other topic that we covered, right? Was wave speed, a stretched string. Let's see, not going. Okay, now it came in. That's the equation that I didn't derive, but you want to see the details. I just brush up over it. That's how we model the string, the wavelength string. Okay, it can be, this section of the string can be approximated to that of a circle. And when we do the derivations, we get that final equation for the speed of the wave. We're going to skip energy and power for wave. We covered the wave equation. That you gotta memorize. That you gotta memorize. It's not difficult to memorize. That's a one-dimensional wave equation. You can have the 2- and 3-dimensional wave equations. Okay, and here's the derivation for that. And what I want to talk about now is the interference of wave. I'm going to skip energy and power of a wave traveling along a string for now. And we're going to talk about interference of waves. The first Okay, so let's take a look here. The first thing that you have to know about interference of waves is how waves reflect and refract. Okay. Again, the level that we're gonna talk about here is a very qualitative level that can be applied to solve quantitative problems. So here you go. Here's one possible wave that you have. This is a pulse, right? And like I said before, like I mentioned before, every wave that we have out there, every possible wave that we have out there can be described as a summation of planar waves. So this pulse that you see right in here can be written down mathematically as a summation, or either a summation or an integral of planar waves. So if you have this pulse propagating from the left to the right, this pulse is going to have an equation that's going to be a function of x minus vt, right? And as this pulse propagates through this medium, which is the string, is going to come in contact with a barrier, a fixed end of the string. Just like you have in the strings of your guitar, right? The strings of your guitar, they have both ends of the string, they're fixed. And the moment we pluck the string of your guitar, we create a disturbance in the medium, which is the string. And a wave starts propagating along this string. Now, when a wave hit this fixed point, something interesting happens. The wave itself is going to reflect, just like light reflects from a glass. This type of reflection can be predicted by the wave equation. We're not going to prove that mathematically here, but the idea behind that, the result behind that is very easy to memorize. What happens when the wave comes in contact with this fixed end? Okay, well, the following happens. The wave gets inverted. It reflected to the left, and now what was a function of x minus vt becomes a function of x plus vt with a negative sign in there because the amplitude now, because the wave is upside down, okay? So mathematically, let's go to the next one, here you go. So mathematically, it's going to be like that. Notes. Reflection First, let's talk about reflection of waves. Okay? Consider a wave traveling from the left to the right on a string. Okay? It can be described as, can be this mathematically described, right? Mathematically described as, whoa. I'm gonna get my one of my equations here. You know, I'm gonna put it y, okay, f x minus vt. And remember what I told you, right? This thing can be any wave, can be described, decomposed, even this, not just described, but decomposed into several, I'm gonna put I here, several planar waves with different amplitudes. That's why it's so important to study planar waves, either in terms of sines or cosines or a linear combination of them. Here I'm gonna just be a little bit case I, okay, x minus dt, like that. Okay. When this wave reaches a fixed point in the other end of the string, it is reflected, and its phase, okay, we call it a phase or orient, is shifted by 180 degrees. What does it mean? It means that the wave becomes upside down. In other words, the wave becomes upside down. Okay? Mathematically, we express that as, and I'm gonna even say, let's see, incident wave. I'm gonna put that like incident wave. INC for incident wave. And then the next one is going to be the reflected wave, right? In the case of the reflected wave coming out of a fixed point, not only the wave is going to be reflected in the other direction, but its orientation too is going to be, the wave is going to become upside down. And the same wave can be described as a summation of planar waves. Now I'm going to erase that because you don't need to know that. Okay? That's a qualitative treatment. I want to remember that, to memorize that. Okay. So here is a reflection of a wave when incident in a fixed point. Okay. What about reflection of waves in a moving point? Not a fixed point, but a movable point, right? We have an illustration of that as well, right here. Here you go. We have my string, but the difference here of this string to the previous one is that it has a this other end here of the string is capable of moving up and down. It's not fixed. It has a little, circle there at the end that can be moved up and down if energy passed through it. So what's going to happen with this wave when it's incident at that point? Okay, the very end of the point is going to move up and down, unlike the other one that has to become fixed because it's attached. Okay, oh, see that? Here's the movie, right? See that? Here you go. Again, the wave is becoming incident at this point because the point is loose to move up and down. It will move as the wave pass through it. Eventually, it's going to reflect again, but it's going to reflect with in the upward direction. Okay. We're doing that free ends, right? We're doing that because there are many waves out there that we cannot visualize that behaves exactly this way. We're doing that for the string, right? Because many of the characteristics of the string we find also in other waves out there. So here you go, going back to my one more student coming. Go. When the reflection of a wave on a free point on a free end. Let's put this way, free end. When this wave reaches a free end, right? Free point in the other end of the string, it is reflected and it's not shifted at all. It's not shifted at all. In other words, if the wave is incident upright, it's also reflected upright. Okay. So mathematically, it's going to be like that. One more student. Here's the incident wave. You don't need that anymore, right? And then it's going to be the reflected wave. Did I put reflected? Yes. It's going to have a propagation that's going to be on the other direction, but its amplitude doesn't change at all. There will be no negative point, no negative sign. Okay. In addition to reflection of waves, we also have refraction or transmission of waves. Okay, when I mean that transmission of waves, it means transmission from one medium to another that has different characteristics. Okay, so let's go here. I want to do the following. Go free end, fixed end. Yeah, I'm going to end it. Okay. The end. Yeah. Okay. Fixed end. Fixed end. I got it. this way. Okay. And then I'm gonna need that as well down the line, just to get it better organized. Okay, and now what you have here is not reflection of a wave, it's a transmission or refraction of a wave. Transmission of waves. The other case, here, you have one medium here, this red line, and another medium here. In this specific case, the black medium has a larger linear mass density than the other one. And it should be not just transmission, but it should be reflection as well, okay? Reflection and transmission of waves, like that. So this medium here, from lighter to heavier, from lighter to heavier string. Okay. So what happens in this case? Though this connection here is free to move up and down, no problem. Okay. But don't forget, this one is a heavier medium, has a higher linear mass density, a greater linear mass density than this one here. So when on the string, when the wave reaches this point, what happens? Part of the wave is transmitted, but then because this medium here is heavier, there will also be some reflection, because not because the medium is heavier, but because the medium is different, there will be a reflection. There will be a reflection. But because also this medium is heavier than the other, the wave is gonna shift its phase. It's gonna become upside down. The reflected wave is gonna be reflected upside down, okay? Then simple enough to remember. And then reflection and transmission of waves, but now from one heavier medium to a lighter one. So the velocity is going to be less as well, because this medium has more inertia. Okay. And what about the other way around? I guess you have already got the idea, right? From the previous one, you already got the idea. You're going to have reflection, you're going to have transmission, okay? Heavier to a lighter string. At this point, there will be some of the wave is going to transmit, and we're still going to have a reflection. But the reflection is not going to shift the phase of the wave at all. Those are the pieces of information that the qualitative ideas that you must have there in your mind. Okay. And I'm going to document that here. Okay. When a wave travels from a lighter medium to a heavier one, part of the wave is transmitted and part of the wave is reflected. The reflection occurs because of the difference between the two media. Okay? If the second medium, right, is heavier than the other, then the reflected wave will be reflected upside down. Right? So here you go. We're going to have something like that. Right? Incident is going to be like that. Reflected is going to be like that. But let's not forget that the amplitude is going to change. This amplitude is going to be less than 1, okay? And then we also have a transmitted wave. Transmitted wave. It's still going to be negative, but here is going to be a positive, right? A prime. That's how we denote both A and A prime, both A and A prime are less than 0. And their amplitude will be, will reflect the conservation of energy. Okay? So if you have, I'm going to write in a different way, okay? Here is the initial wave. If you have here the initial wave, right? The incident wave, which is I'm going to call the initial wave. Why not? The final wave can be written in terms of a reflected wave plus a transmitted wave. Okay? It's a linear combination of those two waves. In order to have conservation of energy, okay, in order to have conservation of energy, the square of the amplitude, the square of the amplitude of the waves must be conserved. And what do I mean by that? More. What I mean by that? Here the amplitude is 1, right? Here's the amplitude is 1. So in order for you to conserve energy in this process, we must have the initial amplitude square. Oh, someone else is knocking at the door. Hang in there. You go. And then what we have? We have that, magnitude of A squared plus, A prime square. Like that. That's a statement of conservation of energy. I don't need to put 1 square anymore, all right? Just to be reminded of that. Okay, the same now. Lighter medium to a heavier one. We are going to repeat. Now you're ready. You should know, right? What would happen if it travels from a heavier medium to a lighter one? And a heavier medium to a lighter one. Part of the wave was transmitted and part of the wave is reflected. The reflection occurs because the difference between the two media. If the second medium is lighter, then the reflected wave will be reflected upright. Okay, incident, reflected, transmitted, and just like before, we have something like that. And again, the energy is going to be conserved. Okay? Those are the ideas that you need to Keep in mind, because now we're going to talk about something called interference, the interference of waves. You have to, before we start talking about interference of waves, you have to understand how waves reflected, right, out of points. Okay, and then we have what we call the principle of superposition. So we did the reflection of a wave on a fixed end, reflection of a wave at a free end, reflection and transmission of a wave from lighter to a heavier string, reflection and transmission of a wave from a heavier to a lighter string, okay? Let me move that right here. So what is interference of waves now? What's the idea of interference of waves? Interference of waves, okay? You have to think about the interference of the waves is that, when waves collide, what happens? Okay. I want to write that down here. When waves collide, okay. Suppose that somehow, suppose somehow that you can have two waves traveling along the same medium. Okay. And I'm going to write that down. One wave is going to be wave one. Okay. Wave one. Going to be y sub m sine, k x minus vt. And the second wave, let's assume that they have the same amplitude for sake of simplification. But then I'm gonna come up with this other wave that's counter propagating. Okay. The resulting wave, you already saw that before, right? Obeys what we call the superposition principle, or y is equal to y1 plus y2. Okay. Or okay. Those waves have the same speed and have the same wavelengths, just for sake of simplicity. Okay. And then we can come up with a simpler relation. There's gonna be, I'm not gonna do that right now, but I'm gonna do very soon. Is it's possible to combine those two sine functions into a single other function that express the same result in a different way. Okay, and we're going to do that. Let's do that after the break. And before we go for the break, I want to take attendance. Okay, so here you go. Eugene is not here, right? Ashley Shu, I don't see Ashley. Zakir, I don't see Zakir. Amy is not here either. Andy? No. Oh, Andy is here, right? Hi, Andy. Just say hi.
Hello, Professor.
Okay, thank you. Alex Hernandez. Thank you. Emily. I don't see Emily. Sartak. Let's see, Sartak. America. Okay, don't see Sartak. And Stephanie. Stephanie's here, right, Stephanie? Just say hi. Okay, thank you. Raise your hand. Good. Zaid. Zaid is not here. Not yet. Okay. Alisa. No, Alisa. Kartika. Hi, Kartika. Are you there? I'm gonna put a star here. Mary.
Here.
Thank you, Mary. And Raymond. Raymond's not here. Ashley. Ashley Thai. Not yet, right? Kyriakos. No, Kyriakos. Alexis.
Hello, Professor.
Thank you. Jeshwan.
Here.
Thank you, Jeshwan. Basilio. Basilio Lopez.
I'm here, Professor.
Thank you. Daniela. Is Daniela here? I don't see Daniela. And we have a total of 8 students because Kartika didn't answer, right? Okay. Kartika. Good. So it's 8:52 right now. Let's go for our break. Break from 8:52 to 9:07, right? Yeah, 9:07 a.m. Okay. So I see you in 50 minutes. I'm back here. So here you go. We have an illustration in your book that shows what happens when waves collide, right? So here you go. We have this forward propagating wave. We have this backward propagating wave in a string. And remember, all this description that you see here applies also to non-material waves, right? So when they start to collide, they're going to either interfere constructively. In this case, their amplitudes are going to add up. Okay, I'll give these just, when they start colliding, right, we start to see this disturbance growing up here. They keep on growing up until they reach maximum amplitude. The point of maximum amplitude occurs whenever the largest amplitude of one wave coincides with the largest amplitude of the other wave. And then, they move about like they had in the original format, right? And we are assuming that there is no losses here, no energy losses in those two waves. In the real world, there is some energy losses, but assuming that there is no energy losses, then what happens, okay? So what we're going to do now, here's the qualitative way of understanding. We're going to do now, we're going to crank up the mathematical formulas for two waves that have the same amplitude, like, and one is propagating the forward direction, the other is propagating in the backward direction. Here you go, right in here. Let's see if we can simplify this relation that we see right in here. Now, all you have to do in order to solve that and put in a simpler format, you have to look at your trigonometric relations that you learn, okay? In math. So I'm gonna write that right in here. Okay, so I'm going to expand. I'm going to expand the argument of both signs. Let's not forget this one is a positive one. And then we have, first we expand the arguments, right? And then we expand the function. You know, sine of a minus b is going to be what? It's going to be sine of a, sine of a times cosine of b. In this case, it's going to be minus kvt, right? Plus sine of b minus kvt times cosine of a. That's our first sign. Then we got to do the same for this one here. I'm going to, let's see. No, I cannot do that. Otherwise it's gonna look odd. And then we have to repeat for the other one. The other one is gonna be quite similar to the first one. The only difference is going to be the negative sign in the argument of the sines and cosines. Make sense? I want to, there's a better way of, let's see if I can get it. You know what? I'm going to put something like that. Here you go. Why? Let's do this way. It's better, right? So it stays in the same line. Sine kx minus kvt, sine cosine, sine cosine. Okay, sine kx plus kvt, sine cosine, sine cosine. And now we're going to try to simplify as much as we can. Let's see what can be simplified. Okay, this negative sign disappeared because cosine of minus theta is going to be equal to cosine of theta. Sine of minus theta is going to be minus sine of theta. And then we don't have to do anything else here. It's already in the format that we want. Is there anything that we can do? Let's compare this term here. I'm going to highlight it. With this term right here, highlighted as well. We see that they disappear, right? So we go for our next step. We cancel out those two terms. And now we are going to have this term here, which is exactly the same as this term here. Simple, right? And then what we get? We get 2. I'm going to put the 2 here. Amplitude sine kx cosine kvt. That's what we get. And now I'm going to write in a slightly different way. First, I'm gonna put this term here, that's the function of time, in front of this other term here, that's the function of position. And then I'm gonna come to you and say, look, folks, what we have right here is something that is a function of time, okay? But it is a function of time, but there's more to it. It's a function of time that varies from -1 to +1, right? That's what this thing is all about. So how can you visualize this type of function? The way to visualize this type of function is going to be a sine of kx, okay? Sine of kx, which has its amplitude, not just sine of kx, but twice the amplitude, the original amplitude of sine of kx, that has its amplitude modulated between 1 and -1, or between -1 and 1. Can you picture that? Try to picture that in your mind, okay? Okay, so, in this case, the amplitude of the resulting wave varies from -2y sub m to +2y sub m. Subscript. So it's a sine wave that's going to be oscillating between those two amplitudes, okay? And I do have a simulation here that illustrates how it happens. This one here, simulations, sound waves. Let's see, it's this one here. Standing wave. It's gonna be something like that. Okay, no, not this one. Let's see, maybe this one. Yeah, maybe this one. Let's see here. Okay, so what we're going to have here, you already saw a simulation, right? Of a forward and backward propagating wave. Okay, and here, what do I have? I have that same expression that you saw. Okay, and I'm going to start with time t equal to 0. Okay, that's how my wave starts. Forward and backward propagating waves are interfering with each other. Let's see. Now this one is too much. Let's go for 0. Let's try 0.5. No, it's too much. Let's see. Gotta play with it until we get there, right? 0.1. Oh yeah, that's right. That's how we gotta do it. You gotta do in steps of 0.1. 0.2, 0.2 seems too fast. Let's start again. 0.05. 0.05, right? Okay. And then 0.1, 0.15, yeah. 0.2, 0.25, 0.3, 0.35, 0.4. You see how it behaves? So 0.4, 0.45, right? 0.5, 0.55, 0.6, okay? That's how it behaves. It's a very nice, interesting behavior. And that's exactly what you see in the guitar, in the strings of your guitar, okay? In reality, the strings of the guitar is just a single lobe, but it is possible to create a string of a guitar in which you have several lobes. 0.8, okay, 0.85, etc. And now we can, I'm gonna go back in time here, and we're going to play this movie again, right? Here you go. Okay, so that's how we get. That's how this wave interferes. Okay. So we can now start playing with this with this equation and learn a little bit more about that. Okay, here you go. Let's get that here. I'm gonna copy and paste here. For instance, one question that I may ask you, I'm even going to put this cosine back there in front. Okay, this cosine, I'm putting that in front just to have an idea that this cosine of kVt is modulating the amplitude of the sine wave. One question that I may ask, right? One question I may ask. No? At which instant of time, the amplitude of this resulting wave is 0 all over the extension of the wave. Okay? At which instant of time? Okay, in order to do that solution, right? You can try to do the solution yourself as well. This term has to be 0. And when a cosine is equal to 0, a cosine is equal to 0 whenever its argument is equal to pi over 2. Okay? Pi over 2, not just pi over 2, but 3 pi over 2, right? 3 pi over 2, 5 pi over 2, 5 pi over 2, right? 7 pi over 2, etc. Pi over 2, etc. Oh. Or another way, you go 1, 2, 3. Another way to express that would be what? Parentheses 2n plus 1. Pi over 2. Pi over 2. Or n equal to 0, 1. N equal to 0, 1, 2, 3, so on. But let's get just the first one for n equal to 0. Okay, here you go. So we go ahead and get kVt equal to pi over 2. We want to find out the instant of time t in which that happens, right? Let's not forget that the k is 2 pi over lambda, angular wave number, right, according to the book. The pi cancel out with the pi. The 2 from the left combine with the 2 on the right. The lambda pass to the right, multiplying this constant, and the v ends up here. What you end up having here is let me put the v like that, right? Meters per second. Meters divided by meters per second is seconds, right? That's the unit. Oh, we can do better than that, right? We can do even better than that. Don't forget that the wavelength, the speed is equal to the wavelengths divided by the period of the wave, right? And look what we get. Lambda cancels out with lambda, and the period of the wave goes upstairs. Neat, right? Very simple result here for this specific wave. If we do the most generic way, right? If you solve in the most generic way, it's going to be what? 2n plus 1 pi over 2. 2n plus 1 pi over 2. Okay. Pi cancel out with pi. Clean it all over again. The 2 combine with the other 2. The 2 on the left combine with the 2 on the right. The lambda. Now I want to do a slightly different way, right? Now I'm going to put substitute the v by lambda here. Lambda divided by t. Lambda divided by t. I'm going to do another step here because I want the lambda cancel out with the lambda. And finally, the instant of time, right, becomes an odd number of t divided by 4. Okay, or let's see if I can get a single lobe vibrating for you, okay? Neat result, right? Let's see here. Here we have 1, 2, 3, 4, 5 lobes, right? In order to decrease the number of lobes, what I have to do is to adjust the wavelengths here of my function. The wavelength from here to here is 20. This guy goes all the way up to 50. So let's say my wave has a wavelength of 50 meters. Okay. How many lobes we get? We get 2 lobes there, right? So in order to get just a single lobe, just like we see in our guitars, I gotta make it the wavelengths equal to 100, right? And now we can start playing the movie. Let's see. Oh, no, I'm not done with that. Here you go. We start with 0. 0 is the point of maximum amplitude. What we did before, we did 0.05, right? I didn't do anything, huh? Let's see. Let's try 0.1. Yeah, very small displacement. Let's see, 0.2. Yeah, okay. Start 0, 0.2, 0.4, 0.6, 0.8, 1, here you go. 1 full second, right? 1 full second. What's next? 1.2, right? 1.4, I'm gonna go a full oscillation, 1.6, 1.8, 2, 2.2, 2.4, 2.6, 2.8, 3, 3.2, 3.4, 3.6, 3.8, 4. That's gonna be our full oscillation. Can we go another 4.2? What happens? And now it's gonna go down. Okay, so that's a full period of vibration, right? Now I'm gonna play it again so you can see more quickly. Okay, here you go. I'm redoing, here you go. So that's how a string, right, of a guitar behaves when you pluck it, right? Just a single lobe. But it's possible to put more lobes there too. The string of the guitar is a little bit more difficult, but we can do that in experiments, okay? This type of lobe that you see here, we call it a fundamental lobe, okay? And now we can start talking about standing waves. You can see that it looks like as though this wave is not going anywhere. It just stays standing there, right? It looks as though it's moving nowhere, this wave. That's why we call it a standing wave. But in reality, we have two waves, one propagating to the right and the other propagating to the left, okay? The wave is not standing, the wave is moving. One propagating to the right and the other propagating to the left, giving you the illusion that the wave is not going anywhere, it's just changing, shifting its amplitude. But in reality, you have two waves there. One counter-propagating with the other. One wave counter-propagating with the other. And now, going back here. Okay. So we did that, right? Yeah. Okay. Say when two waves of same amplitude and of same amplitude and wavelengths collide, right? Wavelengths, let's see, of same amplitude, wavelengths and period collides, right? When I mean collides, they are counter-propagating. They are counter-propagating with respect to one another, right? With respect to one another. We get the illusion that we have a single wave that is standing still. That is standing still and not moving at all. When in reality, we have two waves. One moving to the right, one moving to the right, and the other moving to the left. Okay. Because the wave seems to be steady, not moving at all, not moving at all, okay? We call this type of wave a standing wave. Okay? In the case, in the case, for instance, of the string of a guitar, okay, we get this type of wave because the two ends of the string are fixed. Okay, make sense? The two ends of the string are fixed. When we disturb, right? Disturb the medium, which is the string. Okay. We create a wave. We create two waves. One that propagates to the left, and the other that propagates to the right. These two waves are reflected at their respective fixed points, are reflected at their fixed points. Their amplitude are inverted, and they interfere again, forming the pattern, the standing wave pattern that we see. Right? Their amplitude becomes inverted, and they interfere again, forming the standing wave pattern that you see. This happens over and over again until the amplitude of the wave, until the waves lose their energy. Right? This happens over and over again until the waves exhaust their energy. Become inverted. Come on. Repeatedly here until the wave exhausts their energy. And it looks like we got a big count here. Their amplitude becomes inverted. Oh. And now we can start talking about, so there are, there are different types of standing waves. Okay? There are different types of standing waves. There are different types of standing waves that depends on the length of the fixed string and their frequency of vibration. Let's take a look at that. Okay, so see here. Yeah, here you go. Now we are talking about a wave. Okay, so what we have here? We have wave 1 and wave 2, right? In this specific case here, the waves are in phase with one another, and we end up having constructive interference. See that? Constructive interference here. In this case, the waves are out of phase with one another. That out of phase means 180 degrees out of phase. Then we get destructive interference. And then we have everything else in between. Okay, we have everything else in between. We have those two streams, and then we have everything else in between. Okay. So when the waves are in phase, they interfere. What we say? We say that they interfere constructively. When they are out of phase, they interfere destructively, 180 degrees, pi radians, 180 degrees. Okay. For the case of the wave with fixed ends, right? The fixed end would be here and here. Okay, those points that you see here are called a node. It's called a node. Okay. This is a crest. This is a valley. And let's continue. Okay, so let's see if I have the illustration here for a standing wave. This phenomenon, oh, here you go, I have it. But let's see. Let's see if I have a better one here. Yeah, it doesn't look like I have it. So we can, I don't want to write this. Let's see here. Nope, we don't have it. Okay, so you gotta stick to that one in there. Oh, here you go. I overshoot it. Here you go. So that's not the right illustration, but let me show this illustration here. Here you go. This one is better. Okay, so here you go. Here is a case in which we have a standing wave with two lobes. It's oscillating back and forth. This end is fixed, this other end is fixed as well. Okay, and this one here is the wave with a single lobe. We call that the fundamental mode of vibration. Okay, so consider, consider the case of a string with two ends fixed. Okay, when we get a single lobe, right, vibrating, we call this mode of vibration the fundamental mode of vibration, the fundamental mode. One. Fundamental mode. Okay. When we get two lobes, right, vibrating, we give it the name the two lobes of vibration. We call this mode of vibration the second harmonic. Second harmonic. Okay, three. When we get two lobes of vibration, three lobes of vibration, vibrating, you call this mode the third harmonic, and so on. Third harmonic, and so on. And then there are some other things that we can talk about those modes of vibration. Okay, now consider that the string, that your string that has two fixed ends, okay, has a length of L. Okay, find the wavelengths. Find the wavelengths. Of the fundamental, second harmonic, second and third harmonic. Okay, consider that as an example. This one is a very easy way, it's a very simple type of problem. Doesn't look like simple, but it's a very simple type of problem that you can solve, okay? All you have to do is to make an illustration of those modes of vibration. Here you go. We have here the fundamental mode of vibration. The distance from here to here is L. What's the wavelength of this wave, right? What's the wavelength of this wave? You can see that, L that you see right in here is just half of the wavelength, right? The full wavelength you get whenever you extend this wave to the right. So for the fundamental mode of vibration, there is a straightforward relationship between lambda and L. So here we go. L is going to be what? Even better. No, lambda. Let's do lambda is going to be what? Twice L for two fixed, ends. Then we gotta do it for the other one. You go ahead, draw the next mode of vibration, the harmonic. Okay. You show the two lobes of vibration. Then what happens? This length here is L, and this length L coincides with the wavelength of the wave. Okay. So next, that's the fundamental. I'm going to put lambda 1. Okay. Lambda 1 to denote the fundamental mode of vibration. Lambda 2, which is the second harmonic, is going to be equal to L, right? And then that's when things start to become a little bit difficult, a little bit more complex. Let's see if I have the third one. Yeah, I have the third one here. Now I have 3 lobes of vibration, okay? And then the way I like to teach my students is the following. From here to here is half of a wavelength, okay? 1/2 of a wavelength, 2/2 of a wavelength, 3/2 of a wavelength, right? And then you can employ the same technique in the other two. 1/2 of a wavelength, 2/2 of a wavelength, right? 1/2 of a wavelength is equal to L, right? 2/2 of a wavelength is equal to L. 3/2 of a wavelength is equal to L. This one is for the previous one, right? 2/2 of a wavelength is equal to L in the previous one. So let's write it down. Let's write down in a different way, right? So here you go. 1/2 of a wavelength is equal to L. And then we solve for lambda 1 is equal to 12, right? Here you go. There's a reason why we are doing this way. Then we get lambda 1 is 12. Lambda 1 is 12. And then we go for this other one. 2/2 of a wavelength is equal to L. Then go. Lambda 2 is equal to L. And then you go for the next one. 3/2 of a wavelength is equal to L. Do you see a pattern coming here? Do you see a pattern? We're doing that so we can figure out if there is a pattern or not. Okay, so we have 1, 2, 3. Next, Next in line. And by the way, here's going to be the third harmonic. Here's going to be the fourth harmonic. 4 halves of a wavelength equal to L. It's going to be lambda 3, right? It's going to be lambda 4. And it's going to be 1.5 now. 1.5. Etc. Etc. The genetic formula for this case is, what's the genetic formula? I'm going to get this one here. N half of a wavelength is equal to L. Make sense? Or lambda sub n is going to be 2 divided by NL for n equal to 1, 2, 3, right? And so on. So this relation here that we saw encapsulate every possible wavelength that you get for a standing wave with 2 fixed ends. Okay? And then we can relate that to the velocity and the frequency as well, right? Remember that? We can write that down as well. There are some experiments that requires us to write in this way. 950. One. To L over N. And then, then you can ask us as well. Here you go, another question here, another example. Find, find the position of the nodes of this standing wave. I'm asking the position, right? Find the position of the nodes of this standing wave. We go back, that's another problem. We go back here to our solution. We found the instant of time in which you have 0 amplitude, but now we are going to find out what are the positions in which we have 0 amplitude. Okay, the condition, the mathematical condition for this standing wave is going to be sine kx is equal to 0. We want to find the position. What do we want to find the position? We want to find the x values for which we have this condition, an amplitude equal to 0. Okay, so in order to satisfy this condition, the argument of my sine must be what? 0, pi, 2 pi, 3 pi, etc., right? 3 pi. 3 pi, here you go. 1, 2, 3, and pi, right? For n equal to 0, 1, 2, 3, etc. It all depends on the wavelength. It all depends on the length of the string, right? So here you go. For the first one, for the first node, I'll put it, the first node, the position of the first node, you know what? I'm going to put like that. I'm going to put like in the genetic formula. The first node is, I'll call it the zero node. Let's call it the zero node. The zero node is exactly at the origin, right? The zero node position is exactly at the origin. And then we're going to have, even better, I'm going to put the generic formula before. Here you go. Kxn is n pi. Like that. The zero node is at position 0. The first node is going to be at the position 1 over k, which is what? Lambda over 2 pi. Okay, and that's going to be the first node. The second node position is going to be at 2 divide, wait a minute, there is something wrong. Oh, there's a pi missing, right? There's a pi missing here. 1 pi. Yep. 1 pi. The pi cancels out. One more. This pi cancels out here, cancels out here. And then we're going to have 2 divided by k. And now don't forget the pi as well, right? Pi. Pi. Okay. The second node is a position equal to the wavelengths. Yeah. The third node okay, it's going to be like that. 3/2 over 2. Now it's just a question of, yeah, let's see. Just a question of whether all those nodes are going to fit in the lengths of the string, right? N pi, oh, pi cancels out with pi, and lambda over 2, and lambda over 2. Okay, what are the boundary conditions? What are the boundary conditions? What are the boundary conditions? We have this type of boundary condition, right? F F for x equal to 0 at t is going to be equal to 0. Not only are we going to have this boundary condition, but we're going to have 2 boundaries conditions at the beginning of the string. Because the string has its ends attached, we're going to have this type of boundary condition. And I can go ahead and put 3 dots here. 9:58. Am I missing any messages from you? Let's see, we have 9 students here, and oh, there's more students here arrived. So let's see. Who arrived? Who was not calling my attendance before? Let's see. Kartika, are you there? the Zaid, right? Zaid that arrived. Contreras. Let's see. Zaid, okay. Are you there, Zaid? I'm gonna put a star here in Zaid's name. Do you have any questions? So this part of interference of waves, especially waves that are interfering among each other, is rather, intuitive. It's very intuitive. It's very easy to find all those relations that I just derived for you. Okay, it's 9:59 right now. Okay, and I did this one right now because it's easier. No, and then there are more. There are other types of interference that we're going to continue covering. Okay, so let's take our break from 10 a.m. to 10:15, right? To 10:15 a.m. And I see if you don't have any questions, I'll see you in 15 minutes. Okay. Thank you. I'm going to stop sharing and okay, we're back here and break. Okay. And let's take a look at the book again. Okay, so what we are doing here in this one, what we're doing right now is a mixture of this one with this one, okay? That's what we're doing right now. It's a mixture of those two. Counter-propagating waves. Okay, and then we're going to get into this one very soon. And then the details of this one as well is important. We're going to do that. Okay, so here we go. We did that, right? And oh, I showed that to you as well. Fixed boundaries, right? And free boundaries. The phase is inverted. In the fixed boundary, the phase remains the same in a free boundary. Okay, here you go. Here are pictures of different modes of vibration. Like I said, what we are familiar with is this mode of vibration here in the strings of a guitar. That's what we are familiar, but it's possible too, with the proper equipment, to excite other types of other modes of vibration, right? First harmonic or fundamental mode, the second harmonic, the third harmonic, and so on. And again, this is a type of phenomenon that we see not only in mechanical waves, but other types of invisible waves as well. Even electromagnetic waves, we do see this type of phenomenon in electromagnetic waves. What you see right here is a type of is a phenomenon that we call resonance. Okay, we get a very large amplitude of the wave as it vibrates back and forth, but only certain frequencies are allowed for this type of vibration. Okay, not every frequency, only certain frequencies. Let me give you an example. Okay, let's play a little bit with that, a little bit more with that. And by the way, this is an experiment that I like to do with my students. Let's get the wavelengths. Here we go. That's the one. That's the equation I want. Okay. So we're going to elaborating a little bit more on this concept of resonance, elaborating a little bit more on the case of the modes of vibration in a string with two fixed ends, okay? Recall that there is a relationship between the wavelengths and the lengths of the string, and the two lengths of the string, okay? Okay, the idea is the following. Suppose that we have, suppose that the speed of a wave in a string is v. Okay. We already know that we can have only certain wavelengths for the standing modes in this string. Okay. The question that I make is here, what are the possible frequencies of vibration, okay, in this string of length L, okay? That's the question that I'm making. Another example, treat that as though it is an example. Only certain wavelengths for the standing mode in this string. What are the possible frequencies of vibration in this string? Okay, so here goes the solution. That's the type of problem that's going to be useful in our first lab. Not our first lab, in one of our labs. Okay, so we start here with the wavelengths. Let's put here aside for now. We're going to use it very soon, and then we're going to need another equation. Okay, we're going to need the equation for the speed of the wave in the medium. You already know that only some wavelengths are allowed in this string of length L. Okay, but since the string is made, since each different wavelength propagates in the same medium, okay? Here you go. I'm gonna put even like that. We can recall that there is a relationship between the speed and also the parameters of the medium. Remember that? Is the force of the tension, right? Divided by the linear mass density. So no matter what is the type of wavelength that fit within that length L of the string, speed is going to be the same, okay? It is like to say, you know, the speed of the fundamental mode is going to be equal to the speed of the second harmonic, which is going to be equal to the speed of the third harmonic, provided you are using the same string for all those modes, like that. And then we know that on the right side, we must have a different relation, right? That's going to be lambda n divided by the period of your wave. But in order for this ratio to be equal to a constant all the time for any values of n, the period of the wave must vary from one mode to another. Okay? But I'm not asking about the period. I'm asking what are the possible frequencies of vibration. We have possible wavelengths of vibration in the string, and then we're asking what's going to be the possible frequencies of vibration in that, oh, not here, in that same string, F. Okay, so what we have to do, we have to rewrite our period in terms of the frequency. Do you get the idea? Okay, and here I'm just emphasizing that every mode of vibration has the same speed in a given string. I don't need that anymore. Okay, and then we are going to have this relationship. Let's not forget that my lambda n can be here written in a different way. It can be written in this way. And look what we get. We get, just like we have only certain specific wavelengths are allowed within the string, only certain specific frequencies will be allowed as well. There's gonna be V divided by 2L, like that. 2L. And those are the specific frequencies. I'm going to write that on the other side. Equal, like that. Okay. So if you want to excite, the fundamental frequency, what is the consequences here? If you want to excite the fundamental frequency in your string, you must use its corresponding. You must you must vibrate the string with its corresponding frequency F1, right? Or F1, that's going to be this one. You're going to need an oscillator that has this specific frequency to excite the fundamental mode with that specific wavelength. And the same thing goes for the second harmonic and the third harmonic, and so on. And that's exactly what we do in the lab. We have a device that can adjust, that we can control the frequency of oscillation. We couple this device to a string and specifically and excite that specifically mode of vibration. Okay, and so on. Okay, what I want to do now. So the question is how all of that theory applies to longitudinal waves, right? We did for transverse waves. What about longitudinal wave? How does this theory apply to longitudinal waves? Well, we're gonna get there now. We're going to start covering that now. Okay. First, let me tell you I'm gonna show you a simulation first. See, it's standing wave, must be this one here, right? Okay, this is one. So let's do the comparison here first, right? Before we go for the simulation. Here you go. That's how my longitudinal, not this one. I'm gonna get the other one. Okay. Here's a forward propagating transverse wave. A forward propagating transverse wave, which is the easiest one to visualize. That's the easiest one to visualize. Now, what about a forward propagating longitudinal wave? Longitudinal, it's not much different, right? It's not much different. The only thing that changes is the letter that I'm going to use. A forward propagating longitudinal wave can be expressed in terms not of a y, the y means in the vertical direction, right? But in terms of a net. And I put here, I'm going to put it here, S sub m. S sub m to denote maximum, S maximum, okay? That's how we would describe the oscillation of a single point along a longitudinal wave. And if we go here, let's see. Here we have an example of a longitudinal wave. Let's see if I have a better. Okay, so let's see if we can play a little bit with this one. Instant of time 0. Yeah, here you go. Do you see the wave moving somewhat? So as time goes by, now that's too much. Let's see, 0.5, 0, 0.5. I think it's not enough. Must be 0.25. Let's try 0.25. Okay, okay, yeah, it looks like 0.25 is the way to go. 0.25, 0.5, 0.75, okay? And 1. This is what you see here is actually a standing wave in the longitudinal direction. Let's take a look. Not a standing wave in the longitudinal direction, but okay, must be this one here. Okay. Sound. Now t equal to 0. Let's start. Let's see if it works. 1. No. Didn't do anything. Let's go 0. Maybe it's 0.1. Let's see. Yeah, looks like it's 0.2. Okay, looks like yeah. Okay, do you see the wave propagating from the left to the right? This is an unbound wave, okay? It has no strings, no ends attached. 0.7, 0.8. What you saw before was a longitudinal wave with some boundary conditions. This is an unbound wave with no boundary conditions whatsoever. Okay, and 1, 1.1, 1.2. Okay, do you see we have this illusion that something is propagating from the left to the right. We have this illusion that this specific point is moved, those specific set of points is moving to the right, when in reality, it's not what's happening. In reality, I'm going to show exactly what 1.6, right? 1.7, 1.8, 1.9, 2, 2.1, 2.2, 2.3, 2.4, right? And now I'm going to go back in time. Undo. See the wave propagating backwards? That's because I'm moving the, oh, not here. Here you go, right here. Now I can go forward. Redo, oh, no. Okay, now we got it. Here you go. See that, the wave propagating to the right? We have this illusion that those points that are bunched up in the waves are moving to the right, when in reality, that's not what's happening. In reality, I'm going to show you exactly what's happening. I'm going to get one of those points that I drew here for you. It took me 4 hours to do this simulation here. Select data. No, that's not what I want. Let's see. Trying to remember how to get that trend line. Is that the one? No, select data. Nope. That's not the one. There's a way to change the size of this point. Series, select data, add data label. No, don't want that. Format must be in the graph. With a series, reset match style. And maybe it's here. No, it's not that one. Select data. No, it's not that one either. Oh my goodness, must be in there. This one here. Chart style. Yeah, it must be here. Okay. Data labels. Access title, chart data labels, error bars, legend. Is that the one? Let's see. Right, more options, error bar, data labels, chart title. I gotta, well, I'm gonna do the following. I don't think I need to do that. Just concentrate on this data point that you see right here. Okay? And I'm going to, no, it doesn't stay there. I'm sorry. Is that the one? Maybe chart area. Let me pause the recording for a few minutes. Resume recording. Here you go. What I'm going to do, I'm going to get one of those data points and I'm going to increase its size so we can follow along my simulation what is happening to those points. Okay, see that? I have a bunch of data points here. Each of those data points represents a molecule of air. A molecule of air that's producing the sound that we all hear. You know, here, one molecule of air and one molecule of air, another molecule of air, and so on, okay? Here, this other molecule of air that blew up in size, okay? And I'm going to start my simulation all over again, okay? 0.1, oh, look, watch what happens to this dot that I have there, 0.2, see that? It's not going anywhere. It's just oscillating about a position of equilibrium. And every one of those points are doing that. And in the process is creating that illusion that there is something moving from the left to the right. The something that's moving is not the physical molecule, but it is, like I said, it's the wave. It is the energy associated with that wave, okay? And if I go in even smaller steps, you will be able to see a finer, right? small pieces of motion. Okay, so he go and 2. Let's do that. Now instead of 1.1, let's go 0.05, right? Here you go. Then 0.05, 1.15, 0.2, 0.25, 0.3, 0.35, 0.4, 0.45, and so on, right? 0.5, and now we have a higher resolution in time. Okay, 0.7, 0.75, 0.8, right? 0.85, let's stop at 1, 0.9, 0.95, oh, 0.95, and finally 1. I don't need that here. Now, let's go back in time, right? Here's my time machine. Look at this point. It's just oscillating back and forth about the position of equilibrium. See that? Let's see. It looks like I went too far. Yeah, I went too far. I want to go to 2, right? And now, okay, I want to start here. Okay. Yeah. See that? Oscillating back and forth. And it has a small range of oscillation, a small range of motion. Okay. It's oscillating somewhere between those 2 positions here, right? Those 2 points. Let's take a look at the amplitude of this. Let's see. How close does it get? Okay. So it looks like the further it goes is around here. Okay. And let me mark it. There must be a insert data review homepage layout, maybe. I wish I could put a marking there, but I cannot do that. Break, bring forward, formula data review, view. No, must be home or insert. See, yeah, I want to put, well, we cannot do that, but it's somewhere around here, right? Now let's continue. I'm undoing, right? Let's see how far it goes to the left. Yeah, it looks like it's around here, right? It's around here. So it's oscillating between here and here. That's what it's doing. Let's see what's the amplitude that I put in here. The amplitude that I put here was N2, 0.4. Okay, let's go here. You have two units here. So the amplitude is 0.4. So this distance that you have from here to here is around 0.8, almost half of the distance between the square. So this air molecule, right, is oscillating back and forth like that. The distance from here to here is approximately 0.8 meters, let's say, in my, my scale. And the amplitude of motion right in here is 0.4. Okay. So did you get a good idea? So each of those molecules of air are oscillating like that. But it's oscillating in the direction of propagation of the wave. Instead of oscillating the vertical, it's oscillating in the longitudinal direction, right? In the same direction that the wave is propagating. Okay, so that is my forward propagating wave. Don't forget when I write something like that, I'm saying that it is the position of a single point in that simulation. In general, it's not S1, it's going to be S sub I. Okay, like that. Everything is going to have the same velocity and the same wavelengths. It's a collection of points. By the same token that a string has infinite number of points, in this case too, we're going to have a very large number of points. Okay, that's how we simulate those longitudinal waves. It looks like I forgot to turn on, right? Oh, no, I didn't. It's moving. And then what else can we do about that? We are going to just follow step by step, the same way that we did with the transverse wave. These types of longitudinal waves are also subjected to constructive and destructive interference. Okay? By the same token that as well as resonance, okay? Constructed, destructive, and resonance exhibit this characteristic of resonance and resonance. Okay. The parallel between standing waves of a standing waves in a string and longitudinal waves, right? It's not standing. Let's see, there's a better transverse waves. The parallel between a transverse wave in a string with fixed points, with fixed endpoints, and longitudinal waves. Longitudinal wave also have another. Let's put it this way: longitudinal waves also have a counterpart. Also have a counterpart of a transverse wave in a string with fixed endpoints. Okay. This can be best illustrated by musical instruments, by the way. Okay. Let me elaborate a little bit more what I mean about that. Okay. And by the way, when it comes to sound, this amplitude, I didn't mention that. Okay, very important. By the way, when it comes to sound, okay, the relative positions of the air molecules, affects the pressure at that specific point. Okay, a larger concentration of molecules in a given point, like you have here in this position here, you have a larger concentration, right? those are a larger concentration of molecules at a given point, which are a region of compression, right? Results in a larger pressure. Okay? Likewise, a smaller concentration on a given point in a given region, right? Region. A larger concentration of molecules in a given region results in compression of the molecules, resulting in the compression molecules, which is reflected in a larger pressure, okay? Likewise, a smaller concentration of molecules in a given region results in a smaller concentration of molecules in a given region results in the in a region in a rarefied medium, which is reflected not in a larger pressure but in a smaller pressure. Okay? And this type of longitudinal waves are also subjected to constructive and destructive interference. Constructive, destructive interference, and resonance. So longitudinal waves also have a counterpart. So longitudinal waves also have a counterpart. Also have their counterpart of transverse wave in a string with fixed endpoints. You know, this specifically happens with musical instruments. Okay. Depending how a musical instrument is manufactured, you may have different standing waves oscillating inside the instrument. Okay. So by the same token that you are going to have a forward propagating longitudinal wave, you are also going to have a backward propagating longitudinal wave, which can combine between each other, which can combine among each other to result in resonance at a specific wavelengths and frequencies. Okay. In the case of sound in air specifically, the speed of sound in air is around 330 meters per second. Okay? And just like we mentioned before, the wavelengths and frequency of the sound is related to the speed of the sound. Okay, but don't forget, and that's for any medium. Okay, for an unbound medium, without boundary conditions, right? Without boundaries, you may have any wavelengths. You may excite, right? Excite any wavelengths and frequency. However, inside a bounded musical instrument, only certain wavelengths and frequencies are allowed. Just like in the string with fixed ends, okay? Now we have some, a little twist. There is a little twist for longitudinal waves compared to transverse waves. There's a little twist for longitudinal waves. If we have resonance, if transversal waves, right? Transverse waves can resonate whenever their ends are fixed, comma. For longitudinal waves, we have different conditions. For instance, have you ever seen a musical instrument with both ends closed, right? This situation would be akin, right? Akin to the string with fixed ends. Situation would be akin to the string with fixed ends. So we don't have the situation. What we have actually is musical instruments with one end open and another closed. Okay. And with one end open and another closed, and two, both ends open. Okay, those are the type of conditions that we study. And now the way we illustrate them is in the following way. Here you go. Here's the situation of longitudinal wave inside a cylindrical device that's closed at this end and opened at this end. Okay. Under this condition, molecules here at this end cannot vibrate. They don't have space to vibrate because we have this closed end. Okay, it is as though they are standing still here. So one way to depict that, instead of drawing all those molecules, which would take a long time to do that, right? But the way we do it, we make this analogy with the string. We draw a string to represent, a section of the string to represent the behavior of your longitudinal wave. At this point, the longitudinal wave is not vibrating at all. At this point, the longitudinal wave, the particles in the medium is vibrating a lot. Okay, with maximum amplitude. No, so sorry, is the resulting longitudinal wave has maximum amplitude. Okay, which would be represented by the concentration of points here. Okay, so that's one specific standing wave that you can find in a tube. Okay, and then there's this other specific. See what we have here is the boundary conditions, right? The boundary conditions here would represent a pressure of 0. Okay, and here represent a maximum pressure variation. That's what this representation is all about. And then we have to fit waves within this tube. Here you go. Here is one possible mode of vibration for your sound. Here's another possible mode of vibration for the sound. Remember, we must have maximum amplitude here and 0 amplitude here. Okay. The next one would be like that, and so on. Lobes, 1, 2, 1, 2.5 lobes. Okay. Do you have another one? No, I don't have another one. And we can come up with derivations. And what about, okay, what about 2 ends open? 2 ends open would be represented by that. Okay. That's one mode of vibration. That's another mode of vibration. And so on. And we can derive equations for the wavelengths of those longitudinal waves as well. Okay. Any questions? So don't forget we have particles vibrating here, right? And let me show you the other graph, right? That standing wave here. This one here. Oh, okay, here you go. That's the one I first showed to you, right? Here is the standing wave of a longitudinal wave. Let's see, 1. Now let's go to 0 again. Let's try 0.5. Yeah, it looks like 0.5 is a good one. Let's see 0.3, a little bit. Yeah, okay. 0.3, no, let's do 0.2. Okay, 0, 0.2, 0, 0.2, 0.4, here you go, 0.6. That's how a standing wave looks like in a tube. 0.8, 1, 1.2, okay? Here we have regions of high pressure, and compressions, regions of compression, right? And so on, right? And here we have a region of rarefaction, 1.4, right? 1.6. That's how you should visualize those. 1.8, 2, 2.2, 2.4. Okay, that it doesn't look like this wave is moving, right? Unlike the other one, it's just standing still there. But in reality, we have waves moving to the right and to the left. That gives us this illusion that they are in a standing still pattern, 3.8 and so on, right? So let's go back in time. Here you go. So you can see the simulation. I don't like this one. Let's see. I think I'm going to do better than that. 0. We're going to go step by step of 0.1. Yeah, 0.1 is better. 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, right? 0.8, 0.9. Okay. 1. 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, 2.1. Okay, so this is the point where you have where the longitudinal wave is in the position of zero amplitude. You see, everybody here is that would correspond to the straight string, right? No change in the pressure. That would correspond to a pressure of 1 atmosphere in the air. So all the variations that we see is anywhere between one atmosphere plus and minus a small amount. Okay, change of atmosphere. Here you go. 2.2, right? 2.3. Here you go. 2.4, 2.5, and so on. 2.6. Right? And now let's go back in time. There, okay, now we can go forward. So here you go. Here the oscillation is in a tube. This is in this specific simulation, I didn't put the boundaries here at the end. I didn't do that, okay, in this specific simulation. It's just inside the tube, a region inside the tube that doesn't include the ends of the tube. I didn't go through the trouble of doing that, okay? But let's 1107, right? Let's go until 1115. And let's derive how the wavelengths change for those two conditions, okay? Closed end, right? Closed end and open end. Okay, first case, longitudinal wave inside a tube with a one closed end and another open end. Okay, it's just a matter of fitting the proper waves in there, and I recommend you that we use exactly the analogy of the transverse wave in a string. Okay, so here you go. Here's my first fundamental mode. Okay, you do not have one lobe, you actually have a half of a lobe. And the distance from here to here corresponds to a quarter of a wavelength, right? 1/4 of the wavelength is equal to the length of the tube, right? And then we have the next one. Here you go. 1/4 of wavelengths, 2/4 of wavelengths, 3/4 of the wavelengths correspond to the length of the tube, just like we did for the other one. And then you can keep on going on like that. 1/4, 2/4, 3/4, 4/4, 5/4 of a wavelength. There's another one? Yeah, no, there is not. So let's go. So first case, longitudinal wave inside a tube with one closed end and another open end. Fundamental mode. Fundamental mode is going to be, 1/4 of a wavelength, because it's a fundamental mode. I'm going to put λ1 is going to be equal to L. The next mode is going to be, we gotta go for the drawings, right? The drawings to guide us. If you don't memorize those things, just remember the drawings. The drawings help us. 1/4, 2/4, 3/4. Okay? 3/4 of all wavelengths is equal to L. The next one, 5/4 of a wavelengths is equal to L, and so on. See that? See the pattern? 1, 3, 5, right? 1, 3, 5, 7, 9. So the generic equation should be an odd number divided by 4. 2n plus 1 divided by 4. Even better, 2n minus 1. Let's do 2n minus 1. Okay? Where n all depends on the value of n, the equation. N equal to 1, 2, 3, so on. For n equal to 1 is 2 minus 1, 1/4. For n equal to 2 is 2 times 2, 4 minus 1, 3/4, and so on. Okay? Those are the wavelengths for the first case. And let's rewrite the wavelengths, the generic wavelengths for L divided by 2n minus 1 and minus 1. Now I'm not going to repeat the values of n. I'll leave this way. And now we're going to do for open ends, right? Closed end, the amplitude is going to be 0. Open end, the amplitude is going to be maximum. Maximum positive and maximum negative, right? And now what about open ends? Second case. Second case. Two open ends. So go back to the drawings that you saw that I showed to you. It's easier to memorize the drawings, right? So fit a wave with maximum amplitude at both ends of the tube. That's your fundamental mode for this case. And then what we have? 1/4 of a wavelength, 2/4 of a wavelength is equal to L. 1/4 of wavelengths, 2/4 of wavelengths, 3/4 of wavelengths, 4/4 of a wavelength, 1 full wavelength equal to L, and so on, right? So let's go. Let's identify the pattern. Okay, go. 2/4 of a wavelength. Okay. Then you're going next in line is going to be 4/4 of a wavelength. Lambda 2. Did you get the pattern already? Next one is going to be 6/4 of a wavelength. 1, 2, 3, 4, 5, 6, and so on. If the first one was an odd number divided by 4, the second one is an even number divided by 4. Okay, the even number divided by 4, which can be further simplified to n divided by 2, right? Equal to L. Okay, and I'm gonna go even further than that, because I'm gonna put like 1/2 here. I'm gonna put 2 halves here, which is 1, right? I'm going to put 3 here, but if we do that, we don't quite see the pattern, right? 3 halves. We don't quite see the pattern. Here should be 1 half, 2 halves, 3 halves. That's another way, right? But what is important to remember, right? I did this way just to follow side by side what I have here. If here is odd number divided by 4, here is even number divided by 4. Okay, and then I have to write down the wavelengths in terms of the lengths, like that. Okay, and 11:15, right? 11:16. Any questions? Like I said, this type of treatment, mathematical treatment, also applies to electromagnetic waves. And let's see how many students we have here. I still have 9. Let's see. Oh, we have 9 students. I have only 7 here. Let's see. Zaid, are you there, Zaid? Looks like Zaid is away from his computer. And Kartika, are you there, Kartika?
He raised his hand when you asked him the other time.
I can hear you. What did you say?
Zaid raised their hand when you asked the first time.
Oh, thank you. Thank you. I didn't see the hand raised there. Thank you. Okay, and what about Kartika? I don't see Kartika here now. Andy, he is here. Yeah, Andy, he is here. We have 9, 8. Okay, who else came in? Must be Sartak. Oh yeah, Sartak, are you there? Yeah, good. Thank you, Sartak. I'll give you attendance here. And now we have 9 and 11:18. Let's have our lunch break now. It's 11:20, right? Break from 11:20 to 11:50 a.m. And I see you in half an hour. Okay, I'm back here. So let's take a little break from the equations, right? What right becomes true. Too difficult. It's too difficult to follow and too boring as well, right? And what I'm going to do, that is PBS has this series of physics video crash course in physics. They also have a series of engineering videos as well. And they have stuff about waves, okay? Sound waves, for instance. Number 18, we have number 39, number 40. See, number 39 is about light waves, but light, because the waves also produce interference, right? Spectra, interference and polarization. There is some waves in there, traveling waves, crash course in physics, 17. And let's take a look at those. And there are also, if you go YouTube, you're going to see some neat simulations as well, right? See that? I'm gonna click this one quickly, and then we get into the crash course in physics. Here you go, wave interference, right? This is the type of simulation that I used to do with my software. And this it doesn't. Well, there is some interference going on here in this wave, but it doesn't show what the source. Oh yeah, here you go. Let's go on. Okay, that's one source. See that? Here is one wave propagated, but now we are talking about two-dimensional waves. Okay, so far we talked just about one-dimensional wave, and here is one wave, and the other wave is coming here, is going to interfere with this one throughout the whole two-dimensional space. And look what happens. Okay, as the wave propagates. And by the way, he's simplifying here because he's assuming that the amplitude of the wave doesn't decay, and you get all those neat patterns as we move along. You know, that what you see right in here are constructive, is the pattern of constructive interference. Okay, and anywhere in between here, you have destructive interference. And we also have no interference at all in between. Okay, and that's how complicated this thing can get when you get only two waves interfering with each other. Okay, here you go. Look at this linear, this line coming out. All of that stuff can be derived mathematically. And some time ago, I did something like that with the software. Oh, here you go. Okay, see what's happening here? He's now drawing the position of each source of the wave and the circular wave that's propagating from the source. So it's just like having a wave in a pond. You go ahead, put your finger in the surface of the pond, move up and down, and then you generate that wave, right? The circular wave. And then you get the other finger close by the other one, you know, pluck into the water, you know, can be same frequency, can be different frequencies, okay? And you're going to find, to create this complicated pattern that you see here, where this circle that you see right now can be a point of, you know, can be a region of maximum amplitude of the wave. Each of those circles can be a region of maximum amplitude. The distance between those two circles, each circle is the wavelength of your wave. Okay, wavelengths here, wavelengths here, wavelengths here, right? And then as those circles intersect with the circle of the other source, it forms an interference pattern. Okay. That's one, very quick. Let's see. And this guy that you see right here, I met him some time ago, you know, Professor Dave explained he's a very successful YouTube blogger. He has all sorts of videos in every type of science. He's a chemist by training, but then he also posts videos on physics, economy, and other stuff. Okay. Here, but let's go back to the crash course in physics, traveling waves. You can find other videos about that in the YouTube, and let's take a look at that. Let me pause it momentarily and increase the. Okay. I'm going to start from the zero.
Here we have an ordinary piece of rope. It's not one of those magician's ropes that can mysteriously be put back together when it's cut in half. And it's not particularly strong or durable. But you might say that it does have special powers because it's going to demonstrate for us the physics of traveling waves. Ropes and strings are really good for this kind of thing because when you move them back and forth, movement of your hand travels through the rope as a wave. By observing what happens to this rope when we try to...
What you see right here is a very good model of an unbound wave, okay? In principle, strictly speaking, an unbound wave would have to have an infinite medium. But what you see right here is a behavior of an unbound wave, because this end is free to move up and down. So
physics of traveling waves. Ropes and strings are really good for this kind of thing because when you move them back and forth, the movement of your hand travels through the rope as a wave. By observing what happens to this rope when we try different things with it, we'll be able to see how waves behave, including how those waves sometimes disappear completely. How's that for a magic trick? The typical wave, and waves form whenever there's a disturbance of some kind. Often when something about the physical world changes, the information about that disturbance gradually moves outwards, away from the source in every direction. And as the information travels, it makes a wave shape. Think about the disturbance you cause, for example, when you jump on a trampoline. When you hit the trampoline, the downward push that you create moves the material next to it down a little bit too. And the same goes for the material next to that, and so on. And while that information is traveling outward, the spot where your feet first hit the trampoline is already recovering, moving upward again because of the tension force in the trampoline, and that moves the area next to it upward too. This up and down motion gradually ripples outward.
did you see how she illustrated the trampoline? That's an example of a two-dimensional wave, okay? So here's the medium, the trampoline is the medium, just like the string is the medium of your wave. And this woman here is producing a disturbance in the medium. Okay.
For example, when you jump on a trampoline, when you hit the trampoline, the downward push that you...
The disturbance of the medium. Okay. While she is in touch with the medium, she is disturbing the medium. She is producing, she's applying an amplitude to this elastic medium.
Create, moves the material next to it down.
Maximum amplitude right now, right?
A little bit too.
A little, right here. Right here is maximum amplitude.
And the same goes
and now
for that, and so on. And while that information
she's gonna fly, but then you still have a disturbance in this medium that's gonna make the mid of the trampoline move upwards. Okay, here you go. And look how she depicted the disturbance in this two-dimensional medium, right? We will have, let's say, a lobe here and another lobe here, because the ends of this trampoline is fixed, of this medium of the trampoline is fixed. The amplitude at this point throughout the whole circumference of the trampoline is going to be 0, just like we have for our one-dimensional string, right? And that, look at the mode of vibration, right? You have this type of mode of vibration, illustrating this type of mode of vibration. That's going to be 1 wavelength and a half.
Okay. The trampoline is already recovering, moving upward again because of the tension force in the trampoline, and that moves the area next to it upward too. This up and down motion gradually ripples outwards, covering more and more of the trampoline, and the ripples take the shape of a wave. Waves are made up of peaks with crests, the bumps on the top, and troughs, the bumps on the bottom. They have an amplitude, which is the distance from the peak to the middle of the...
Yeah, the amplitude, just like we described, and here is the node of the wave, in which you have no displacement whatsoever.
Wave. They also have a wavelength, which is the distance
from peak to peak. And don't forget, it's a sinusoidal wave, right? The easiest one to understand, a planar wave.
Between crests, a full cycle of the wave, and a frequency, which is how many of those cycles pass through a given point every second. Multiply the wavelength by the frequency and you get the wave speed, how fast it's going. And the wave speed only depends on the medium it's traveling through. That's why the speed of sound, which is a wave, doesn't depend on the sound itself. It doesn't matter how loud or quiet it is. It just depends on whether the sound is traveling through, say, air or water. Now, there are four main kinds of waves, and we can use our rope to show the difference between some of them. A pulse wave is what happens when you move the end of the rope back and forth just one time. One lonely crest travels through the rope. That's the pulse. Then there's the continuous wave, which is what happens when you keep moving the rope back and forth. In that case, your hand is acting as an oscillator. Anything that causes an oscillation or vibration can create a continuous wave. Now, things that cause simple harmonic oscillation move in such a way that they create sinusoidal waves, meaning that if you plotted the waves on a graph, they'd look a lot like the graph of sine x. But the waves we've mainly been talking about so far are transverse waves, ones in which the oscillation is perpendicular to the direction that the wave is traveling in. When a wave travels along this rope, for example, the peaks are perpendicular to the rope's length. The same thing was mostly true for the waves that you made on the trampoline. The waves were traveling along its surface horizontally, but the peaks were vertical. But there's also longitudinal.
Okay, here's another illustration of a longitudinal wave, right? I didn't mention that before, but think about a slinky, right? A slink, you can produce a longitudinal wave with this link. And sound waves are a very good model of this type of wave that is illustrated here in this link, okay?
Waves.
There you
So
go.
the oscillations happen.
Now, what's happening here? Here we have a standing wave for a this longitudinal wave, okay? Because those two ends are fixed, there is no vibration here at those 2 points, okay? And the wave is, and the motion, the back and forth motion, the oscillating motion of each point are confined to this region outside those 2 points.
In the same direction as the wave is moving. In the case of a longitudinal wave, the back and forth motion is more of a compression and expansion. These are the kinds of
compression and expansion, right? Compression for air, you produce a higher pressure, okay? Expansion of the air molecules produce a lower pressure, and everywhere else in between would be equal to the atmospheric pressure. So let's say compression is going to be 1 plus a small amount of pressure. Our rarefaction would be a 1 minus a small amount of pressure.
the waves that you get by compressing and stretching a spring. And they're also the kinds by which sound travels, which we'll talk about more next time. But all waves, no matter what kind they are, have something in common. They transport energy as they travel. At a microscopic level, waves occur when the movement of one particle affects the particle next to it. And to make that next particle start moving, there has to be an energy transfer. But how can you tell how much energy a wave has? Well, remember that an object in simple harmonic motion has a total energy of 1/2 times the spring constant times the amplitude of the motion squared, which means for a wave caused by simple harmonic motion, every particle in the wave will also have the same total energy of 1/2 Ka squared. All of this together tells us that a wave's energy is proportional to its amplitude squared. In other words, if you double the wave's amplitude, you get 4 times the energy, triple the amplitude, and you get 9 times the energy. So why is the relationship between amplitude and energy transport so important? Well, the intensity of a wave is related to the energy it transports. More specifically, its intensity is equal to its power divided by the area.
Okay, we still didn't talk about power of a wave yet, okay? But remember the definition of intensity. Power, right? Energy per unit of time divided by area.
Spread over. And power is energy over time. So changing the amplitude of a wave can change its energy and therefore its intensity by the square of the change in amplitude. And this relationship is extremely important for things like figuring out how much damage can be caused by the shock waves from an earthquake. But waves also get weaker as they spread out because they're distributed over more area. A spherical wave, for example, one that ripples outwards in all directions, will be spread over the surface area of a sphere that gets bigger and bigger the further the wave travels. The surface area of a sphere is equal to 4 times pi times its radius squared. So as a spherical wave moves further from its source, its intensity will decrease by the square of the distance from it. 2 meters away from the source, and the intensity of the wave will be 4 times less than if you're 1 meter away. 3 meters away, and it will be 9 times less. That's why being just a little bit further away from the source of an earthquake can sometimes make a huge difference. Now let's go back to the waves we were making with the rope. Suppose you attach one end of the rope to a ring that's free to move up and down on the rod. Then, with your hand, you send a pulse in the form of a crest, rippling along it. When the pulse gets to the end of the rope slides along the rod, but then it slides back to where it was. That motion, the sliding back, reflects the wave back along the rope, again as a crest. But something totally different happens if you attach the end of the rope so it's fixed and can't move. Now, if you send a pulse along the rope, it will still be reflected, but this time as a trough. The wave was inverted. That's because when the pulse reached the fixed end of the rope, it was trying to slide the end of the rope upward, but it couldn't because the end of the rope was fixed. So instead, the rope got yanked downward, and the momentum from that downward movement carried the rope below the fixed end, inverting the wave. Now, sometimes multiple waves can combine.
Okay, that's interference. Combination of multiple waves. Okay. Two identical pulses, both crests along a rope, one for each end. Here you go.
Say you send two identical pulses, both along a rope, one from each end. When the two pulses overlap, they combine to make one crest with a higher amplitude than the original one. That's called constructive interference. The waves build on each other. Now let's say you do the same thing again. This time both waves have the same amplitude, but one's a crest and the other is a trough. And when they overlap, the rope will be flat. It looks like the waves just disappeared. That's called destructive interference, when the waves cancel each other out. Constructive and destructive interference happen with all kinds of waves, pulse or continuous, transverse or longitudinal. And sometimes we can use the effect to our advantage. Noise cancelling headphones, for example, work by analysing the noise around you and generating a sound wave that destructively interferes with the sound waves from that noise, cancelling it out. There's a lot more to talk about when it comes to the physics of sound, but we'll save that for next time. Today you learned about travelling waves and how their frequency, wavelength and speed are all connected. We also talked about different types of waves, including pulse, continuous, transverse and longitudinal waves, and how they all transport energy. Finally, we discussed reflection and interference. Crash Course Physics is produced in association with PBS Digital Studios. You can head over to their channel and check out a playlist of the latest episodes from shows like Physics Girl, Shanks Pipette, and PBS Space Time. This episode of Crash Course was filmed in the Dr. Cheryl C. Kinney Crash Course studio with the help of these amazing people, and our equally amazing graphics team is Thought Cafe.
Okay, so that was Crash Course number 17. Okay, and see that? Did you notice that they organized just the same way that I did organize the course? First, they talk about simple harmonic motion, and then they talk about waves. So she just, put in 7-8 minutes, less than 8 minutes, what we have been covering for the past 12 hours, right? Almost 18 hours. That's but of course, she didn't solve any mathematical problems. So let's see. Let's take a look at this here sound.
Todo mundo se encaixa no Gimba. Acabaram as cápsulas de café da Gimba.
Good.
When you think about it, you probably receive hundreds, even thousands of cues about what's going on in your environment every day, strictly from sound. In addition to things like speech and music, there are other bits of auditory information that shape your day. An ambulance passing by, a baby crying in the next room, and of course, sorry, just got a text. But there's a lot we can learn, not just from what these cues mean, but from how sound itself works. Studying sound waves has helped doctors learn more about our ears, and has allowed engineers to design things like microphones and speakers. Biologists have even used the science of sound to figure out how animals like elephants can communicate over long distances when we can't even hear them doing it. It all comes down to the fact that sound is a wave which travels through a medium like air or water. And knowing that sound is a wave is important because it means that we can use the physics of waves to describe the qualities of sound. When you think of a wave, you probably think of the kind you see at the ocean, or the ones you made when you jumped from that trampoline last time. Those waves produce ripples that run perpendicular to the direction that the wave is travelling in. But sound is the other kind of wave. It's a longitudinal wave, meaning that the wave's back and forth motion happens in the same direction in which the wave travels. Say you get a text message on your phone and it makes a nice bright little ding sound. What actually happened? Like on a physical level, your phone speaker contains a diaphragm, a piece of stiff material, usually in the shape of a cone. When you got the message, the electronics inside the speaker made the diaphragm move back and forth. which vibrated the air around your phone. That made the atoms and molecules in the air move back and forth. Then those moving particles vibrated the air around them, and as the process continued, the sound waves spread outwards. Sorry, I'll turn this off now. Anyway, physicists sometimes describe sound waves in terms of the movement of these particles in the air, in what's known as a displacement wave. But by moving particles in the air, sound waves also do something else. They cause the air to compress and expand, which is why sound waves are sometimes described as pressure waves. As the wave spreads through the air, the particles end up bunching together in some places and spreading out in others. Together, all that bunching and spreading out causes areas of high pressure and low pressure to form and move through the air. It's useful to describe sound waves as pressure waves because we can build devices that detect those changes in pressure. That's how some microphones work, for example. They use a diaphragm stretched over a steel compartment, and as sound waves pass by, they create areas of lower or higher pressure in the compartment. The differences in pressure cause the diaphragm to move back and forth, which electronics then translate into audio data. And your eardrums basically work in the same way. As pressure waves pass through, they make your eardrum vibrate. Your brain then interprets those vibrations as sounds, but not all sounds are the same. Even before we knew much about physics, humans were describing sound in terms of certain qualities, mainly by things like loudness and pitch. Our understanding of those qualities helped shape the development of music, which we'll talk about more next time. But there's also a more physicsy side to those qualities of music. Pitch can be high or low, and it corresponds to the frequency of the wave. So air that's vibrating back and forth more times per second will have a higher pitch, and air that's vibrating fewer times per second will have a lower pitch. Humans hear sounds best when vibrations...
Did you hear what she said? High pitch and low pitch. Let's repeat that, okay? Let's repeat what she said.
Loudness and pitch. Our understanding of those qualities help shape the development of music, which we'll talk about more next time. But there's also a more physicsy side to those qualities of music. Pitch can be high or low, and it corresponds to the frequency of the wave. So air that's vibrating back and forth more times per second will have a higher pitch.
Okay, high frequency, high pitch, right?
And air that's vibrating fewer times per second will have a lower pitch.
Lower frequency, lower pitch.
Humans hear sounds best when vibrations are somewhere between 20 per second on the low end and 20,000 per second on...
Okay, that's the dynamic range of the human ear. We can hear sounds that vibrating between 20 hertz and all the way up to 20,000 hertz or 20 kilohertz. That's easy to remember, right? 20 and 20, right? 20 and 20. And then, you know, cats and dogs, you know, they can go all the way down up to ultrasound. Bats and dolphins, even higher frequency, 160 kilohertz. What about elephants and mole? They work in the infrasound region of frequency. We're somewhere there in between. Okay, infrasound, elephant. That's how elephants communicate, right? They use infrasound. We don't hear it. We don't hear it. The human ear cannot hear anything less than 20 hertz. That's why it's called infrasound. And that's how the wavelength infrared is called infrared, because it has a frequency lower than the frequency of the red wavelength. The frequency of the red light, not the red wavelength, but the red light. Ultrasound, right? Higher. Infrasound, lower. Oops.
By a baby crying in the next room, and of course...
Okay, I did something here that I should have done.
Not just from what these cues mean.
Let me get you to the right spot. Accidentally, I changed the position of the video. Let's see, here you go. We want to be here, right?
This is somewhere between 20 per second on the low end and 20,000 per second on the high end. As we get older and lose more of the cells that help us to detect sound, we start to lose the ability to hear the higher pitch sounds. Some building security companies will take advantage of this using devices that emit a high-pitched noise that most people over the age of 25 can't hear. The idea is that since kids and teens can hear it, and it's super annoying to them, They won't hang out near the building. But some sounds are too high or low for any humans to hear. Sounds that are too high in pitch are called ultrasonic, and the sounds that are too low are called infrasonic. Dog whistles, for example, use an ultrasonic pitch that's too high for us, but is perfectly audible to dogs. Elephants, on the other hand, use infrasonic sound to communicate with each other across long distances. They can hear these calls from several kilometers away, but we can't hear them at all. Another aspect that shapes sound is its loudness. When you increase the intensity of a sound, you increase its loudness and vice versa. We've talked about the intensity of a wave before. It's the wave's power over its area measured in watts per meter square. We've also said that the intensity of a wave is proportional to the wave's amplitude squared. And the further you are from the source of the wave, the lower its intensity by the square of the distance between you and the source. And just as there's a range of pitches that humans can hear, there's also a range of sound wave intensity that humans can hear comfortably. Generally, people can safely hear sounds from about 1 picowatt per square meter up to 1 watt per square meter, which is about as loud as a rock concert if you're near the speakers. So sound waves coming from a jet plane that's 30 meters away, for example, probably have an intensity of around 100 watts per meter square. Now, I don't know if you've ever been that close to a roaring jet plane, but there is a reason why the people that work on the tarmac at airports use those heavy-duty headphones. Below 1 picowatt per square meter, sounds are just too soft for us to detect them. And although we will hear sounds above a watt per square meter, they tend to hurt our ears. So here's the weird thing about loudness and intensity. It's not a linear relationship. Generally, a sound wave needs to have 10 times the intensity to sound twice as loud to us. This relationship holds true as long as the sound is towards the middle of the range of the frequencies we can hear. So instead of directly measuring the loudness of sounds by their intensity, we use units called decibels, which are based on bells. Bells convert a sound wave's intensity to a logarithmic scale, where every notch on the scale is 10 times higher than the previous one. The scale starts off with an intensity of 1 picowatt per square meter, corresponding to 0 bells. So a sound that's 1 bell is 10 times as intense as a sound that's 0 bells, and a sound that's 2 bells is 10 times as intense as a sound that's 1 bell, but 100 times as intense as a sound that's 0 bells. Measuring everything in bells can be kind of annoying because sometimes you want to talk about sounds that are, say, 3.4 bells without having to deal with decimal points. That's why most of the time you'll hear the loudness of a sound described using the more familiar decibel unit, a tenth of a bell. To find the loudness of a sound when you know its intensity, you take the base 10 logarithm of its intensity over the reference intensity of 1 picowatt per square meter. Then you multiply that number by 10 to get the sound's decibel level. We can use this equation to convert the intensity of that noisy rock concert, which we said was 1 watt per square meter, to decibels. First, we take the base 10 log of 1 watt per square meter over 1 picowatt per square meter. Now, 1 divided by 1 times 10 to the minus 12 is just 1 times 10 to the 12. So what we really want to do is take the base 10 log of 1 times 10 to the 12, or a trillion watts per meter squared. What a logarithm asks you to do is find the power that you would need to raise the base to in order to get the number in parentheses. In other words, we're looking for the exponent of 10 that would equal 1 times 10 to the 12, which is just 12. To finish off the calculation of decibels from intensity, we multiply that value, 12, by 10 to get the decibel level of the rock concert where you were standing. 120 decibels. Ow! You'll notice that as the source of the sound moves closer to you, it gets louder, and as it moves away, it gets softer. That makes sense, since the closer you are to the source of the sound, the greater the intensity of the wave that hits your ear. But have you ever noticed that the pitch of the sound changes too? It's called the Doppler effect. As the source of sound moves towards you, the pitch of the sound you hear increases, and as the source moves away, the pitch decreases. To see why, imagine you're standing on the sidewalk when suddenly you hear an ambulance siren start up. It's coming from down the road and it seems to be moving towards you. The ambulance is continuously emitting sound waves at a certain frequency in the form of that siren. But as the ambulance moves towards you, the ambulance is also moving towards those sound waves. So the peaks that hit your eardrums are closer together, even though they're moving at the same speed, and you get hit by them more often, which means that you hear a higher pitched sound. At the same time, it keeps emitting more sound, which adds more peak to those earlier sound waves that were heading your way. What you end up with is a sound wave with a higher frequency than before. That's what hits your eardrum, so you hear a sound that's higher in pitch than the one you heard when the ambulance was further away from you. As the ambulance passes you and starts to drive away down the road, the opposite happens. Sound waves are still coming towards you, but the ambulance is driving away from them. So the peaks that hit your eardrum are farther apart.
See the wavelengths here? It's longer than the wavelengths in front of the ambulance, right? See, the wavelength here is shorter wavelengths, higher frequency, longer wavelengths, lower frequency. That's the Doppler effect we haven't talked about yet.
The opposite happens. Sound waves are still coming towards you, but the ambulance is driving away from them. So the peaks that hit your eardrum are farther apart and you hear a sound with a lower pitch. The Doppler effect isn't only unique to sound waves, it happens with light too, which means we can actually use it to measure the distance of stars. But more on that much later. For now, you learned about sound waves and how they move particles back and forth to create differences in pressure. We also talked about pitch and how the intensity of a sound wave changes with amplitude and distance. Finally, we covered decibels as well as the Doppler effect. Crash Course Physics is produced in association with PBS Digital Studios. You can head over to their channel and check out a playlist of the latest episodes from shows like Growth Science, PBS Idea Channel, and It's Okay to Be Smart. This episode of Crash Course was filmed in the Dr. Cheryl C. Kinney Crash Course studio with the help of these amazing people, and our equally amazing graphics team is Thought Cafe.
Okay, so the next one is sound, right? Then we can stop here and then we go back to this video some other time, okay? And what I want to do now is I want to go back to our derivations here. And let's go here to the book first, right? So we cover transverse waves speed and stretched medium. We skip this one for now, the wave equation, interference of waves. Okay, interference of waves. We didn't cover it completely. We covered only part of it. Okay, and we covered standing waves, and we still have to cover phasors. Phasors are a very interesting technique. Okay, so let's just go quickly through what we just covered here, standing waves, okay? So we did that for transverse waves, just like this one. And okay, here is a two-dimensional wave pattern. Okay. Here is the node position. That's the trampoline. Cattle drum head, kind of a trampoline, right? Visible by dark powder sprinkled on the drum head as the head is set into oscillation at a simple frequency by a mechanical oscillator. So there's a mechanical oscillator here at the upper left of the figure. Oh, that's the upper left here. That's the mechanical oscillator. The powder collects at the nodes, okay, which are circles in straight lines in this two-dimensional example. Okay, and you gotta make sure that you get the right frequency here. It's not any frequency that will create something like that. Okay, just like in the string, right? It's not every frequency that will create this type of standing wave here. You must have a specific frequency to do that. And that's an experiment that we do in real life, in the lab. By real life, I mean in the lab. Okay. And what I want to do, I want to go back to this one here. Okay. And it's going to be from the mathematical point of view, what we are going to do now is going to be a little bit more difficult than those standing waves that we have been talking about, okay? And what we did so far. Notes, going back here. Okay, so far, we look at the mathematical model of two waves that are counter propagating, that counter propagated two counter propagating waves. Counter propagating waves. That's what we did. Okay. But what if, in this case, one wave travels in one direction, and the other wave travels in the other direction. Okay. Now, what if the two waves are moving exactly in the same direction, but instead they are just a little bit phased out. They're just a little bit out of phase. Here you go. Out of phase, okay? That's exactly what we have here. The waves are still colliding, they're still interfering, but the difference is that in the first case, they are having a head-on collision, and in the other one, they're just, pass by each other at a different angle, at an angle that's, I call it a phi, okay? Phase angle phi. And by the way, your book has an illustration. Interference of waves right in here. Interference of waves, let's see. Yeah, here the waves are in phase. In phase means what? That their phase difference is equal to 0. Here the wave, and under this condition, we have a constructive interference. In this case, they are completely out of phase by 180 degrees or pi radian. When that happens, you have a completely destructive phase. And then you have something else in between. Here, the phase angle is not 0 nor 180 degrees, but it's somewhere else in between. Okay? You're still going to have an interference, and we want to derive an equation for this genetic condition. Okay? It's possible to do that. It's a little bit more complicated, but it's possible. And what does it mean? It means that one wave is going to have this relation here for the argument, and the other wave is going to have exactly the same relation the first term, because they're propagating the same direction, but we have they're a little bit phased out, a phase equal to phi. Okay, let's see if we can come up with a simple equation when we combine those two waves, right? When we sum those two waves, y1 plus y2, that's y1, that's y2. Okay, there is a nice mathematical trick that we can use to simplify this summation. And this mathematical trick is this one that you see right here. Okay, so here you go. I'm gonna put a little bit of, sine of alpha plus sine of beta, is equal to this relation that you see here. Half of alpha plus beta, half of alpha minus beta. And then you have a sine and a cosine. You can do that yourself. You can prove that on your own, right? You want me to prove that for you? Let's do that. Okay, so 2, right? I'm gonna come up with, gonna be lots of work, okay? And sine of alpha divided by 2 plus beta divided by 2, right? It's gonna be what? Sine of alpha You know what? I think I'm gonna do in my software, in my favorite software, whatever. It's gonna take forever for me to do that. But that relationship is found in any book. Okay, and oh, where is my favorite web? Live Mass. So here you go. We have there's an algebraic manipulator software that I like to use a lot because it saves me lots of, lots of time, half, right? No. Half of alpha, no. Like that, no, oh boy. Let's see if that changes here. Now we got it, alpha plus beta. Okay, and then we have that other relation, which is alpha minus beta. Okay, he didn't do it right. It has supposed to be half. Okay, I'm going to expand those two arguments. We're just going to prove that relationship, right? Expand into expand here. Expand the relationship. And the next thing that we're going to do is to apply that transform. Yeah, that's a transform. Sine of A plus B, right? And sine of A minus B. That's sine of A plus B. That's sine of A minus B, right? Sine of A plus B, as you remember, as you have memorized, is the sine of the first argument times the cosine of the second argument, and then the sine of the second argument times the cosine of the first argument. The other one is exactly the same. The only difference is that the beta factor is going to have a negative sign here and a negative sign here. Consequently, the sine of half of beta is going to be negative. Okay. And transform, let's see if we can transform that. Nope, cannot transform that this way. Okay, and then let's go back. We want to and then we have to, this one is multiplied by the other, right? 2 sine of alpha minus beta. And alpha, sine of alpha plus beta. Okay, so substitute here. Substitute here. And it's going to get, a big thing here. We're going to have this square and sum it. Expand. We gotta expand it. Factor maybe? No. Simplify. Expand. Yeah, it's not doing it for some reason. But anyway, Anyway, what you're gonna get here is the cosine square of half beta, sine square of half alpha, okay? And then you can apply those relationships, sine square of a plus cosine square of a equal to 1. You know, that's the whole process that's gonna lead to what we have in there, okay? I'm gonna stop here, but for some reason my software is not, let's see, simplify. Yeah, it's not doing what I want to do, unfortunately. Apply, no apply. Yeah, even the expand is not doing, but let's leave it this way, okay? So we continue with that derivation that we have here. And why are we doing that? We're doing that because I'm gonna call alpha this term here, and I'm gonna call beta this other term here. And then we do something like that, something interesting happens. Okay, kx minus vt plus kx minus vt plus phi, right? And what's going to happen? You know, those kx minus vt are going to add up, and it's going to cancel this half term. Whereas in this case, there will be a subtraction, and it's going to get much more simpler. Okay? So here you go. See the two here that I mentioned to you? This kx minus vt and kx minus vt leads to this two here. Okay? Which is going to cancel out with this half there. This other part of the cosine are going to cancel out with each other. And the only thing that's going to be left over is the phase term. It's the phase term, okay? And look what we end up getting. We end up getting something that's easier to interpret. We're going to get an equation that's easier to interpret. We have like a cosine of the angle phi, in terms of the angle phi divided by 2, and a sine of whatever you have here plus pi and a half angle. Okay? That's the relation that we end up getting. Now let's see. Let's reduce to our case. What if phi is equal to 0, right? What if the waves are in phase? Let's see if we get what we expect to get. What if phi is equal to 0? I will phi equal to 0 here. I'm gonna, it becomes 0. This one becomes 0 as well. And then cosine of 0 is 1. And what we get? We get twice the amplitude. We have constructive interference of the original wave, right? And so what we saw before is just a special case of this formula that you see right here. What about 180 degrees? 180 degrees here. 180 degrees. Okay. Cosine of 180 is minus, right? Oops, minus. Oh, you don't need that. And then we have this case here. And let's see here. Oh, yeah, it's divided by 2, right? Is 180 divided by 2. So it's not 180 degrees, it's 90 degrees. Okay. Okay. And then we have a better relation, something like that. Okay. Okay. And now we can start studying, right? What's going to happen? Let's see, wait a minute, let's see. Oh, yeah. Oh, yeah, okay, I made a mistake here. Okay, so 100, don't forget, it's 180 degrees divided by 2, right? If it's 180 degrees divided by 2 here, it's going to be 180 degrees divided by 2 here as well. Okay, now we get what we want. We get a 2a cosine of 90 degrees. 2a cosine of 90 degrees. Sine of that. But cosine of 90 degrees is going to be 0. Cosine of 90 degrees is going to be 0, and we have complete destructive interference, no matter what the other term is. No matter what this term is, okay? That's so instead of doing all this derivation, all this messy sine, cosine derivation, we can use something else. We can use a graphical technique, a graphical / vectorial technique to obtain the same result. Let me show you how it works. And that was the chapter on phasors here is all about. The very useful technique, okay, that we use in electricity and magnetism as well. The way it goes is like that, you know. Instead of writing down the sign of kx minus omega t, we just represent our function in terms of a vector that rotates in the plane, okay, on the xy plane. And the projection of this vector that you see right here along the y-axis is the same, exactly the same as the sign of kx minus omega t. The length of this vector is equal to the amplitude in the of your sine kx minus omega t. Okay. Let's see if I gotta have one other one here. Let's see. Not here. We use this technique all the time. Oh, right here. Okay, better. Okay. Here is my phasor. My phasor diagram is represented by this vector, and the projection of this vector along the y-axis is nothing but one of my waves. Okay. If this vector makes an angle of phi, we say that the wave also has a phi phase there along the axis. Okay. as time goes by, right? As time goes by, this argument becomes smaller, and this vector rotates in the clockwise direction. Can you picture that? Okay, for a given kx, right? The vector keep on rotating in the clockwise direction, just like here in the book. Let's oops. No, I don't want like that. Phasor right here. Oh boy, let's see. Oh yeah, here you go. Yeah, now you got there. Phasor, yeah. That's the phasor diagram. Right here. Okay. At a given instant of time, at a later instant of time, correspond to the amplitude of 0, right? So this phasor is rotating about this origin. Why am I introducing this idea? Well, I'm introducing this idea because this phasor technique is very convenient for determining the result of an interference of two other waves. Instead of doing all that mathematical derivation, right? We just go ahead and come up with this phasor diagram representing one wave and the second wave. In this case, they would have the same amplitudes. And the resulting summation would be this net vector that you see here. See that? The resulting vectorial sum is going to be the amplitude of 1. That would be the vector of 1 plus the vector of 2, and that would be the resulting vector. So here in this case, those two waves has a phase difference equal to 5. And the resulting interference wave will have this other phase that you see right here. Okay, if we go ahead and do the triangle, you have a phi, right? Phi angle here. And now you can apply, in order to find the resulting, right, the resulting wave, you can apply the law of cosines to this resulting triangle. Let's do that. Okay, so I'm going to put it aside. Okay, I have another illustration, slightly different illustration right here. Okay, the phi angle difference between the two waves. This wave, for instance, is at a point that has a 0 phase difference, and this other wave has a phi phase difference. The resulting wave is going to have a phase of beta given by this vector here. Okay, and the A prime, okay, here you go, A prime. This argument is going to be the same. This A prime is found from the cosine, the law of the cosines. And I'm going to write that down here for you. I'm going to copy also. I prefer my own graph. Here you go. My own illustration. Phasor. You know, consider Oh, that's heavy. Okay. Consider two waves having two waves of same amplitude, same wavelengths, same speed, having a phase difference phi. Okay. Find, oh gosh, find the resulting wave using a phasor diagram. Phasor diagram. Okay. Here you go. I'm gonna write that down, copy from somewhere else. You go this one here. Here you go. Here's this. Here's my first wave. A. Here is my second wave. Y2. Okay. My resulting wave, just right from the bat, right? This one is rotating in a clockwise way direction. This one is going to rotate the clockwise direction. So consequently, this one is going to rotate in the same direction. Okay. So my resulting this applies only for waves that have the same speed, okay, and propagating in the same direction, same speed, same wavelengths, and propagate in the same direction. And you can also do different amplitudes, right? Okay, my resulting wave will be, resultant wave R A prime, and instead of phi here is going to be an angle beta. Where? Okay, here's my triangle, right? My A prime is going to be given by where? A prime square equal to A square plus another A square minus, twice the amplitude of each wave cosine of the angle. Okay, would be this angle here. A prime square is A square plus A square times 2 times A times A times the cosine of this angle here. Okay. And this angle is going to be what? Notice that the phi angle, the dawn phi angle is this one. Consequently, this angle that you see right in here must be pi minus phi. Cosine of pi minus phi. Yeah. Okay, and we're gonna go for another step. Here's gonna be a square. Nope, two twice. Ah, yeah. Here goes. The 2 goes here. And then we can expand this cosine. And there's gonna be 2a square as well. I don't need that. Okay, and let's see if it fits here. I'm gonna put that in evidence. 1. We don't need that anymore. And then I gotta expand this term. Okay. So what is that going to be? Cosine of pi. Cosine of minus phi. Oops. Minus phi. I'm going to put between parentheses, so I don't get mistaken, right? Then we're going to have a minus sine of pi. Sine of minus phi. Okay. One more. Cosine of pi is what? Minus 1. I'll put, oh gosh. Whoa. I gotta put this one in this square. Okay, now we go for it. That's gonna be minus 1. You go minus 1. And cosine of minus phi is gonna be cosine of phi. I wanna get rid of this little square there that's bothering me. Here you go. Now I got it. Sine of pi is going to be 0. Okay. And then minus is plus. 0 disappeared. Right? That's my amplitude. That's the amplitude that I got. I can go one more step. There's a square of the amplitude. I can go one more step here. That's going to be a square root. Like that. The question is now, how does it reduces to the other solution, right? Let's take a look at the other solution that we got. The genetic solution. Writing here. That's the, that's the amplitude that I'm getting. Okay. Is this term here equal to this term here? That's the question that I'm asking. Okay. Let us see if it's equal or not. Okay, there's a way to prove that this term is equal. Yeah. And how do we do that? Well, we have to here write my cosine of phi in a different way. You write that as phi over 2 plus phi over 2. And then we go ahead and, expand this summation. Is going to be cosine square of phi over 2 minus sine square of phi over 2. So the question is the above equal to our previous solution? Our previous solution? And then we put a question mark right in here. Well, let's see. There's a way to prove that. And now that I have uncovered this relation, I'm going to apply it right here. Right? So place in here, and look what a nice thing I'm gonna get. 1 minus sine square of phi over 2 is gonna be what? Is going to be cosine square of 5 over 2. Right? And 2 cosine square of 5 over 2, 104. We need to go for a break very soon, right? This 2 is going to multiply the other 2. It's going to become 4 cosine square of pi over 2 or 5 over 2. And then bingo, right? We get 2 cosine of 5 over 2. Okay. So yes, the phasor diagram technique can be used to get the same result. Okay. Can be used to get the same result. And what else? Let's see here. My beta here, right? And I can find out what the beta is as well. This is an equilateral triangle, right? This is an equilateral triangle. So from the above triangle, we have what? We have that beta plus beta. Since it's an equilateral triangle, this angle must be beta as well. Plus pi minus phi must be equal to pi. Okay? Must be equal to pi. And now, the pi that is on this side cancel out the pi that's on the other side. The beta that sum up with the beta becomes 2 beta. And then what do we get for beta? We get for beta exactly what we expected. Pi divided by 2. Okay, and my solution right here becomes 2a cosine of 5 over 2 plus 5 over 2 at the end. Okay. So that's what we use for that's how we can apply this technique of the phasor diagram. Unfortunately, we cannot, we cannot use the phasor diagram for counter-propagating waves because one phasor would be rotating one direction, the other phasor would be rotating the other direction, okay? But it can be used for multiple waves, not just wave number 1, 2, and number 2, but wave number 3, 4, 5, and so on, okay? Unfortunately, we cannot use the phasor diagram for two counter propagating waves. Because one phasor would be rotating one direction, the other phasor would be rotating in the other direction. And I'm going to erase that because we already covered everything here. Okay. And we can go for our break. Any questions about that? Let's take a look here at the book. 18, 19, let's see, 16. Okay, so we did transverse wave speed on a stretched string. We didn't do that yet. The wave equation, interference of waves, phasors, and standing wave and resonance. We did almost everything, right, in this chapter. With the exception of this energy and power in a traveling wave. Okay, so if you don't have any questions, let's go for our 15-minute break, and then we go after return, we go for our final 35 minutes break between 1:10 p.m. and 1:25 p.m. Okay, so see you soon. Okay, so 1:27 right now. So let's just review what we did. It can be very overwhelming, right? What we have done so far today. But if once we summarize what we did, that may help you clear up better your mind, right, about what we did here. So let's go back. At the beginning, right? At the beginning of the. Okay, those are the chapters, and we did the interference of waves, phasors, and standing waves. Oh, the only thing that's left is this one here. So what I'm going to do, I'm going to summarize what we did so far. And okay, well, Yeah, transverse wave. Okay. So what are waves? What are waves? Waves is a disturbance. We usually say that's a medium, disturbance in a medium, but it doesn't apply to electromagnetic waves, okay? It doesn't apply, this definition doesn't apply to electromagnetic wave. This definition does not apply to electromagnetic waves. So wave is a disturbance in a medium through which each infinitesimal point of the medium oscillates about a position of equilibrium. Okay. The oscillation of the whole medium gives rise to the appearance of something moving from the beginning of the medium, moving throughout the medium, right? From one end of another, throughout the medium, okay? From one point to another of the medium, moving from one point to another one of the medium. This motion, okay? This motion is associated with the transport of energy, okay? So if you are smart enough, you may be able to tap into this energy. Tap into the energy. And by the way, this definition does not apply to electromagnetic waves. Okay, in the case of electromagnetic waves, what are electromagnetic waves? It's not a disturbance in the medium. For the case of the electromagnetic wave, okay, let's write for this case, this type of wave is a disturbance in the electric and magnetic field. So it's not a medium per se. It's those fields, those electric and magnetic fields, they don't make up a medium at all. So it's a disturbance in the electric and magnetic fields. Okay, I'm gonna put right in here. Waves are disturbances, right? In a medium. So there are transverse waves, which are the easiest one to understand. Transverse waves and longitudinal waves. Longitudinal waves, which is more difficult to understand. A little more difficult to understand. The speed of the wave depends on the properties of the medium. Okay. Although there is a genetic equation for this speed given by the wavelengths and the frequency. Okay? So in the case of just an example, right? We saw the example. In the case of wave propagating along a string, the speed is the speed. The speed depends on the tension the string is subjected to. The medium, I'm not going to put string, but the medium is subjected to, and the linear mass density of the medium. In the case of the electromagnetic wave, its speed depends on the electric and magnetic properties of the medium. For the case of vacuum, these electric and magnetic properties are the constant epsilon naught and mu naught, okay? For the case of the vacuum, these properties are epsilon naught and mu naught, right? Epsilon naught, these properties are dependent on the electric and already did that. For the case of the vacuum, these properties are epsilon naught and mu naught. Epsilon naught and oops, mu naught. That's the one more student coming. We're just summarizing here everything done, right? Wave equation. What's the wave equation? Wave equation, the wave equation is a partial, the PD, right? PD, partial differential equation whose solution is the, I say the amplitude, right? You can say that. No, it's not the amplitude exactly. Is the shouldn't be the amplitude because the amplitude is the largest displacement. Okay, let's say is the displacement, right? Of the parameter that, here you go, let's do it this way, that describe the medium, okay? Displacement of the parameter from its origin, from its position of equilibrium, right? That describe is the displacement of the parameter from its position of equilibrium. Let's put this way. Example, right? In the case of a wave in a string, right? The solution is the position of each point of the string with respect to the position of equilibrium, and that I call y. Is the position of each point of the string, y, with respect to the position of equilibrium. Okay. Examples. In the case of sound, the solution to the wave equation is the pressure, right? Is the pressure variation in the medium with respect to the atmospheric pressure, to the regular atmospheric pressure, right? In the case, example, in the case of an electromagnetic wave, in the case of electromagnetic wave, and we're going to cover that into more detail, of an electromagnetic wave, the solution to the wave equation is both the electric and magnetic fields at a given point in time, and so on, okay? And so on. That's wave equation. Oh, and by the way, it's not difficult to memorize the wave equation, right? I want you to do that. Wave equation. Wave equation. Remember, it's gonna be a second order partial derivative. Second order partial derivative, d wrong, right here. D wrong. Like that. Oh, I don't want that. I'm gonna do that. D tx2, right? Tx2 on one side, dy dt2 on the other side. Now is a question where the constant, and you already know that it's going to be a v square, but the question whether the v square is on the left or on the right side, right? You can find out where the v square is going to go just by doing a dimensional analysis. Here you have 1 divided by meter per second square. Here you have 1 divided by seconds square. So if I put my v square on this side, but downstairs, we end up having exactly the same dimensions on both sides of the equation. This is a summary. Okay, summary, right? Wave equation, interference of waves. Interference of waves. When two waves collide, whether it's a front collision, whether it's one wave catching up with another, whether it's one wave coming, intersecting each other at different angles. That's what the interference of waves is all about. You have constructive interference, destructive interference, and everything else in between. Constructive interference, constructive interference, destructive interference, and everything else in between. So one constructive interference, destructive interference, and everything else in between. That's 0 degrees phase difference. 180 degrees phase difference, and everything else in between. In between 0 and 360, right? It should be 0, between 0 and 360 degrees. That's what phasor. And by the way, don't forget waves. I should write down here too. Waves can be mathematically described in a genetic sense as any function of x plus and minus vt. But the most important types of waves, are planar waves that are a function of sine and cosine. So either one, something like that, you know. I'm gonna put here y is my wave, very genetic, and then we have here a planar wave that's given by a term k, x plus and minus vt. Can be a cosine as well. If you want to be picky about that, you can add a phi angle here, a phase angle here. And this phi can be anything between 0 and 363 degrees. Okay, planar waves are the most important one. Planar waves are the most important ones because they can be used to describe any type of wave just by adding different planar waves like that. Wave equation. What else do we need here? Phasor. Oh, we gotta talk about phasor, right? But let's talk about standing wave first. Standing waves. Standing waves. Standing waves are the interference of two counter propagating waves. The interference of two counter propagating waves subjected to boundary conditions, okay? And what's boundary conditions? Depend. And the boundary condition is going to depend on the type of wave, okay? Subject to boundary conditions. For instance, a string of length L with two fixed ends, okay, are said to have boundary on, are said to have the following boundary conditions. Okay. It's equal to LT equal to 0, right? And X equal to LT equal to 0 as well. The amplitude is 0, the amplitude, the value, not the amplitude, the value, right? The value of the wave is 0 at those 2 points. So you have boundary conditions and initial conditions. You should be more familiar with initial conditions from physics 37, right? In physics 37, remember in physics 37, we have those problems. We had those problems of initial conditions, right? Like X at time t equal to 0 equal to blah, 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 right? And then not just X, and then the initial velocity too. No, V at t equal to 0 is equal to blah, 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 right? Acceleration at time. Those are initial conditions. But now we are talking about boundary conditions. Boundary conditions are the conditions at a given point in space. Okay? Boundary conditions are the conditions at a given point in space. Whereas initial condition is the value of a given quantity at instant of time t equal to 0. So that's a very important situation. Okay, so very important piece of information. So we talked about strings with 2 ends attached, but what about sound waves in a musical instrument, right? Have 2 different boundary conditions, and we abbreviate by BC. We can have one, an instrument with one closed end and another open end. Let's say instead of an instrument, let's put a cylinder, right? A cylinder and a cylinder with 2 open ends, 2 open ends. You can also, state that maybe we can create an instrument that has a cylinder with 2 closed ends as well, right? If you can create a situation in which a cylinder has 2 closed ends and still can provide sound within it, then the boundary conditions of this one would be very similar to the boundary condition, would be the same boundary conditions you have here. Okay. In this case, okay, well, first case scenario, right? The boundary condition, set one boundary condition would be X equal to 0 at time instant of time equal to 0. If it is a closed end, the displacement from the equilibrium position is going to be 0. Whereas for the other end of the instrument of length L, it's going to be maximum. Right. Maximum for a given t, by the way. It's not the maximum amplitude. No, it's not the value of the amplitude. No, it's maximum for a given instant of time, t. Okay. Don't mistake that maximum value as being the twice the amplitude. No, it's not twice the amplitude. It's maximum value for a given instant of time because we have a standing wave. The maximum value at a given instant of time is not going to be necessarily equal to twice the amplitude, right? I can even go back here to my illustrations. Be this one here. Is this one, let's see. No, not this one, standing waves, maybe, no. This one, okay, this one. Okay, let's go for this one, right? Twice the amplitude is this instant of time right in here, right? And 0.2. Yeah. Twice the amplitude of each wave, right? Each wave has an amplitude of 0.1 in this case. So that's the maximum amplitude of your standing wave at any instant of time. However, at a given instant of time, right, 0.5, right? This is the point of maximum amplitude at this instant of time. And that's where this point is going to lie at the open end of your instrument, of your cylinder. That's the important difference to make. That's an important point to make, okay? Maximum value for a given instant of time. That's the first case. Second case. Maximum value, two open ends, right? Maximum value at a given instant of time. Maximum value at given instant of time. So we can even do like that. And let's say this third case, let's see if we can come up with a cylinder that have two closed ends. Consequently, the value of your wave is going to be 0 at those two ends of the cylinder, okay? That's what we have. And what else? Phasors, and finally phasors, right? Let's talk about phasors. Phasors is a vectorial approach to find the interference between the vectorial technique, let's put it this way, the vectorial technique in the XY plane used to find the parameters related to the interference between two or more waves. This technique is best used whenever the waves have the same speed, wavelengths, same speed and wavelengths, and travel in the same direction. They may have different amplitudes. Okay, so that's the summary of what we did today. Hopefully I'll be able to cover energy and power traveling in a wave very soon. And we have 2 minutes to go. Have any questions? 6 hours doing that, right? It's lots of work. Can be very tiresome for you, right? But do we have any questions? I have 1 more hour to stay around because I still have my office hours here. If you don't have any questions, then we can stop here and I'll see you again tomorrow. Thank you for being here.
Thank you, Professor. Have a good day.
You too.